So let's go ahead and get started. My name is Saikat Guha. I'm the director for the Center for Quantum Networks at the University of Arizona's College of Optical Sciences. And my colleague, Christos Gagatsos, he's a research professor at the College of Optical Sciences and will be joining the ECE department starting February in the University of Arizona. Today's course is called the Information in a Photon. It's modeled after two courses that Christos and I teach at the University of Arizona. One is called Information in a Photon, which is actually open to undergraduates with no background necessary in quantum mechanics, but we do require a former background in traditional undergraduate mathematics, such as linear algebra, probability theory, complex numbers, calculus, and so forth. And Christos teaches another course called the Photonic Quantum Information Processing, and that course does require some prior background in graduate level quantum mechanics. And that course is about the mathematics behind the theory of quantum optics. And the course is catered towards developing mathematical tools to understand quantum properties of light and bring the student up to a point where they can use all those tools to do research in all areas of information processing in using photons in the context of communications, sensing, imaging, and so forth. So this obviously is a 3.5-hour course, so we will not be able to cover everything, but our intent is to give you some flavor of those mathematical tools and just to have you appreciate how classical and quantum light works differently in terms of when they interfere with each other, how you manipulate them, how you detect them, and what that means in terms of the efficiency with which information can be encoded, processed, carried in light. So let's go ahead and get started. A few initial logistical points. So Brianna just put a Google Doc link. This is my personal Google Drive link with the slides. So feel free to go ahead and download those slides and have them ready to go in your computer. So that way you can flip back and forth during some of the problem solving sessions. We will have 2 modules and there are 4 questions in each module. The questions always will be multiple choice, although you'll have to work out some math. And we'll give you about 5 minutes for each question. And Brianna is going to put up a Zoom poll so you can pick an answer A, B, C, D. And then once we have a sufficient number of people answer, then we are going to reveal the right answer and then we're going to move forward. And that's probably it. And Brianna is going to share with you the slides on the CQN's central website. The Q&A is open to everybody. We'll try to tag teams. So Christos will try to answer the questions during my portion of the talk, and then I'll do the same during his portion of the talk. So let me share my screen. So I'll have you, Brianna, confirm if you can see the right screen.
Right now we're looking at your calendar. There we go. We're in presentation mode. If we could, or
which mode are you seeing?
I'm seeing if you swap displays. Sorry.
Okay,
there you go. There we go.
Yeah.
Yes.
Okay. So let's go ahead and get started. Our course is called Information in a Photon, and let's start with just a quick preview of the field of quantum information processing. You have been attending this winter school, which is funded by the Center for Quantum Networks. The goal of our center is to upgrade the internet, hopefully someday to be able to carry quantum data or qubits from one point to another. And this new service that's going to be added to the internet will enable a lot of new services or new applications that span communications, security, computing, and sensing. In this course, you will see some applications to communications where using quantum techniques or quantum processing within the confines of the optical receiver can give you better ability to tell apart between states of light, which is applications, for example, to deep space communications. One of the well-known applications of quantum information processing is security, where the promise of security lies in the laws of quantum mechanics, as opposed to our perceived hardness of solving certain math problems. There are many applications of quantum computing that I'm sure a lot of you have heard about: factoring, various types of search algorithms, optimization algorithms, being able to perform quantum computing on a cloud-based server without the service provider knowing what they computed for you. It's kind of the quantum equivalent of fully homomorphic encryption. Various types of multi-party privacy preserving computations or secure computations. And then simulations of complex quantum systems, such as that occur in molecular system, protein folding, and so forth, where the system itself is quantum. So it is inefficient to solve them or simulate them on a classical computer. At the University of Arizona, we have quite a large group of faculty members who are working on various topics surrounding sensing and imaging, using light to get information about the scene, both in passive imaging, where your object or the scene is either naturally illuminated or it's just reflecting off sunlight, for example, in astronomy, or in microscopy or space domain awareness applications. And also in active photonic sensors, where you send out light that could be structured or generated in a more thoughtful way towards the scene, and then you look at the reflected light back. We all have heard about LiDARs that are used in self-driving vehicles, but there are also other examples such as atomic force microscopes that are used for surface topography measurements, fiber optical gyroscopes using a laser light going inside a Sagnac interferometer, and so forth. One of the things that made up a lot of news last few years is the use of non-classical states of light, especially squeezed light, which Christos is going to describe to you today. So hopefully by the end of the lecture today, you will understand what it is. In the LIGO, which is probably the largest interferometer that exists, which was designed to detect tiny modulations to the gravitational waves that are generated by big events far away in the galaxy. And then applications such as magnetic field sensing that have applications to detecting tiny signatures of magnetic field perturbations due to neuronal spiking patterns in your brain, or testing microelectronic chips because their current flowing in the chips can create a magnetic field that you can sense, and then in turn use that to get a tomography of the electronic chip. So in all of these applications using non-classical states of light and non-standard quantum measurements can give you better performance than classical methods. So what is photonic quantum information processing? So basically this field of photonic quantum information processing it has to do with wherever light gets used in encoding, extracting, carrying, or processing information, whether it be it in communications, sensing, imaging, computing, or simulations. When you cast the problem, when you cast the state of light in the language of quantum mechanics or quantum physics, you suddenly have access to a lot of powerful tools that can tell you what is the best possible performance that is permissible by the laws of physics. And when I say best possible performance in the context of communications, it could be asking the question, what is the best rate at which you can send information? Or what's the minimum probability of error with which you can tell apart a few code words that are modulated in laser light pulses? In the context of sensing, a best performance could be what is the best resolution with which you can resolve the angular separation between two stars you're looking at in an astronomical setting? Or what is the minimum mean squared error of sensing, say, a little perturbation in on your reflected laser light from a rough surface where you are trying to make a very fine measurement of a surface using an atomic force microscope. So all of these questions, there is a very nice way to ask these questions using the language of quantum optics and quantum information, where you can get this answer on what is the best possible performance. And then you can compare that best possible performance with the performance that is achievable using the conventional system, and then try to figure out how can you bridge that gap, or whether there is even a good enough gap to be bridged using tools from quantum optics. So speaking of quantum optics, what is quantum optics? You know, Mike Raymer, who is behind this, the Winter School, has conceptualized this whole idea. He's one of the pioneers in the field. him and many others in the field over the last many decades have looked at understanding what happens when you study electromagnetic fields or Maxwell's equations, which I'm sure all of you have encountered in some form or the other, but within the realms of the laws of quantum physics. Nonlinear optics is a field that is central to quantum optics. Nonlinear optics is when the medium through which your light is propagating has a, for example, a refractive index, which is not constant and which can be a function of the intensity of the light within the medium at that point. And when such a thing happens, you can write down input-output relationships of field propagating through such a media. But then when you go and try to do experiments in the lab based off of that classical theory of nonlinear optics, there are certain regimes where the classical Maxwell's equations, their solutions don't match what you see in the lab. And when I say what doesn't match is that there are situations where you can see some light at the output of a nonlinear crystal being pumped by a laser, which classical theory does not predict. But if you do a full-blown quantum theory of that field propagation, it does predict correctly that output light, but the properties of that output light, for example, the statistics of photo detection on such light that is created by such a nonlinear crystal, cannot be predicted by the classical electromagnetic theory or semi-classical theory of photo detection. So quantum optics emerges out of nonlinear optics, and then it spans not just to nonlinear optical materials, but also to atomic systems, such as electron spins in a silicon vacancy color center that is used as one of the most prominent mechanisms to encode a qubit, which is our form of way of encoding a qubit in the Center for Quantum Networks for building quantum repeaters. And also there's a huge field of many body physics, people who work on condensed matter theory, statistical mechanics. They look at how many quantum systems in an array, what are their collective properties, phase transitions, and so forth. And again, this whole area of quantum theory of understanding how light interacts with matter is the area of quantum optics. And then there's a field that called information theory, which really emerged from some of the stalwarts like Claude Shannon, Alexander Holevo, Carl Hellstrom, and many others in the area who quantify the information in the context of communication, sensing, and computing that may not seem to have anything to do with quantum optics. But this whole area of photonic quantum information processing is a beautiful merger of the theory of quantum optics on one hand and this information theory on the other hand. There are 4 bullet points I've written here that, broadly speaking, I still consider them as part of broadly what is considered information theory. And the first one is detection theory, that is a set of mathematical tools that tell you how well can you tell apart between different hypotheses. Estimation theory, set of mathematical tools that tell you what is the most high precision that you can achieve in estimating a parameter embedded in a signal that you are receiving. Data compression tells you what is the best compression ratio that you can have in representing information that has been given to you in some form, either like an image or voice or video. Many of you, I'm sure, have heard about various types of data compression algorithms that are available for that are like WinZip or other applications like that. And then channel coding, which is another field of information theory that tells you how can you send the most amount of data reliably across a noisy medium. And this theory underlies communications that happens in our cell phones or in the Zoom call that we are having right now. Now, all of these 4 bullet points, there are classical versions of these theories. But there are also quantum mechanical extensions of these theories, where you can ask these same exact questions that I just talked about, but say that what is the best possible performance you can have if you don't make any assumption on how the information bearing light in the context of detection, estimation, data compression, or channel coding is detected. And that is gets us to quantum detection theory, or quantum estimation theory, and quantum data compression, and quantum channel coding. Well, so in this course, we will be talking mostly about detection theory in the first module. And the objective of this course is to introduce you to some of the mathematical tools behind quantum representation of both classical light and certain non-classical states of light that Christos is going to go into, and how you can use these tools to understand how quantum and classical light, they behave differently when they interfere with each other, or when they are detected by detectors. And then we'll give you just some glimpses of showing how you can use the quantum techniques for improved performance in encoding, transmission, and processing of information. So we'll go ahead and get started with module 1. And as I said, we'll have some multiple choice questions interspersed through the course, and then we'll end with a post-lecture survey as usual. We will have a 5-minute break in between the two modules, and also one break within each module when you'll be solving the questions. All right, so let's go ahead and get started. So module 1 has to do with quantum limits of information encoded in classical light. So in module 1, we will not talk about quantum light. We'll just talk about laser light, which is the most common form of light source that we are all familiar with. But we will be looking at quantum techniques in detecting information encoded in laser light. This call that we are having right now on Zoom, my voice signal, which is an analog signal, is going through many different steps, traversing through the internet and getting to your home and coming out of your computer speaker. What are the steps that this information is going through? Well, this analog signal that coming out of my mouth is a pressure wave sound signal. It's being transduced by my laptop's microphone into an electrical voltage signal, which is also an analog signal, but an electrical signal. And then that's getting sampled. So you're only retaining the value of this electrical signal at some periodic time steps. And each of those samples is an analog number again. It's a voltage number, which is then getting quantized into a few levels, for example, a certain number of bits. So each of those samples, let's say in this case, I'm showing getting quantized into 4 bits, or a sequence of zeros and ones. So there are 16 levels that I'm quantizing each of the samples in. Well, in some cases, information might already be digitized. For example, let's say you're sending a stream of zeros and ones that are coming out of a computer that is already digitized. Then you don't have to go through these 3 steps that I talked before. Now, almost always, before you send this information onto the channel, you go through another step that is called error correction. So you encode this information. So take each of those, say, packets of 4 bits that I've shown here, and you encode it into a longer stream of bits. So this is an example of a rate half code, where you take 3 bits and encode them into 6 bits. So I'm adding redundancy to my information. Now, once you're done with that process, the next step is modulation. Modulation means that you take each of these zeros and ones, and let's say I'm showing binary phase shifting modulation. So every 0 is being encoded by a laser light pulse of some mean energy with a pi phase shift, and 1 is being encoded with a no phase shift. And then this is your modulated code word, which is then sent over the noisy channel. And then when it's received on the other side, after going through noise and attenuation through the medium, you then have a receiver that converts that optical signal back into the electronic domain. And oftentimes the receiver has 3 portions of it. It has a optical processing, and then there's a detection step. The detection step is what converts the optical signal from the photon to the electron. And then oftentimes there is some amount of signal processing that has to happen in the electronic domain. And all of that together, it generates your the estimate for the code words that were transmitted. Now here, some of the bits that were transmitted appear in error. So the blue ones I'm showing were randomly, they were flipped. But this is where the magic of error correction comes in, that despite some of these bits being decoded in error, the message comes out hopefully correctly if the amount of redundancy that you had added was commensurate with the noise in the channel. And then after you get those digitized information back, then it has to go through the same set of steps in reverse. So you go through interpolation, then filtering, and then a transduction back from your computer's electrical signal to a sound waveform using your speaker, and then you're hearing back what I'm saying, hopefully plus some tolerable amount of noise, so you can understand what I'm saying. So all of this has to go through in any communication system of either radio frequency or optical and so forth. Now, we will not talk about quantum communications in this course, but quantum communications, which is the heart of Center for Quantum Networks, it is a center that is developing the tools and techniques and physical subsystems and error correction schemes, routing protocols, and so forth, to replicate this whole thing that I just talked about, but not for sending bits, but to send qubits reliably over the channel. So those qubits still have to be modulated using light, and then decoded, demodulated, and so forth. In this course, we will stick with classical communications, but what we are going to play with is this piece here, the receiver, that decodes, demodulates this received signal. So before even I tell you all some of the details of the mathematics that we will go into, let me just give you straight an example just to see the kinds of things you will be able to do, with the mathematical knowledge that we will talk about in this course. So let's say that your receiver is receiving one of these 8 code words. Each code word is a sequence of 5 pulses, 5 time bins, where you either have this bit, the 0 or the 1 bit being modulated using a laser pulse of a given energy with a 0 or a pi phase shift. And n is the mean photon number of each of these pulses. Now, you know this code book, you know exactly which one of the, so there are these possible 8 code words that you can receive. So as you can see, there are 5 bins, there are 32 possible sequences, 2 to the 5. But of those 2 to the 5 is 32, you only have these 8 code words that are in your code book. So you can design your receiver with that knowledge in mind. Now, if you were to detect each of these pulses, detect meaning you have a receiver that receives that laser pulse, and then you do something to it that converts that into electrical domain, which we'll talk about some detection formats in this course. And then follow that with some electronic post-processing that asks which of the code words that were received. And by the way, this is how all of the conventional optical receivers work. They go, symbol by symbol detection followed by some electronic post-processing. The best possible receiver that works that way, its probability of error of telling apart between these 8 code words as a function of the mean photon number in each of these pulses is given by this, shown by this blue line here. But then if you use the quantum detection theory, this is detection theory, remember the first bullet point under information theory that I'd written, where you get to ask what is the best possible error probability of telling apart between a few hypotheses. The quantum detection theory, it tells you, well, there ought to be a receiver that gets you, say, 2 orders of magnitude lower error probability at mean photon number of roughly 1 per pulse. And mean photon number per pulse being 1 photons is a very, very legitimate regime. It's a very interesting regime, in fact, for, say, deep space communications. For example, there was a program called the Lunar Lasercom Demonstration led by MIT Lincoln Lab back in 2013, where they set up a lasercom link between the Earth and the Moon. And the received pulses were roughly about 1 photon per pulse. But the question is, how do you design a receiver that gets you this 2 orders of magnitude lower error probability? I will not go into that receiver design in this course, but you have these slides. You can look at this paper over here that we published last year, and a demonstration of that in a trapped ion quantum processor this year. But the main idea is that at that point, your receiver looks like a tiny little quantum computer. Your receiver has to act collectively on all those 5 temporal bins together in a collective fashion. We call them joint detection receivers. There's no way you can even mathematically describe the action of that receiver as detecting every single pulse at a time. By, again, remember, detecting means converting the optical signal into the electronic domain, followed by any electronic post-processing. The receiver has to act collectively on all 5 pulses together. So the optical receiver at that point is a mini quantum computer, and we show that quantum circuit and that transduction step that needs to happen before that, where you load each of these pulses into a qubit, and then the quantum computer acts on those 5 qubits. Okay, so with that preview of the kinds of things you're going to be able to do, I'm going to jump back to some basics, and we will get started with some mathematical understanding of detection of laser light. So here we are all familiar with random variables. We are going to talk about a random process instead of random variable. So a random process of a very specific kind where discrete events happen in continuous time or space. So where can such random processes occur? Where, well, neuronal spiking patterns in our brains, discrete time events or that happen on a continuous time space. People's arrivals in a bank's teller queue, or any other queue for that matter. People are arriving at different timestamps. There are discrete events happening in a continuous time. You have a laser light pulse, you're detecting photons. Photon arrivals, those clicks can happen at discrete times, but over a continuous time. Random processes can also happen in space as opposed to time. Now, a random process of this form is called an arrival process, and this I of t is an instance of a random process. I'm just showing just to depict what it looks like. So we denote these arrivals by delta functions, and these are random timestamps t1, t2, t3, and etc., where the arrivals occur. And n of t is the integration of the I of t from 0 up until some time t. And this looks like a step function. So wherever an arrival occurs, you just jump 1 up. So the value of n of t at capital T, which is let's say the end of time, is the mean number of arrivals. And we will use the letter lambda of t to denote the arrival rate. So lambda t is the number of arrivals per second, for example, and n is the mean number of arrivals over from 0 to t. If an arrival process has a constant rate, then lambda t will not be a function of time, and n will be simply lambda times the total time. Now, a specific kind of arrival process that we will be concerned with is the Poisson point process. It's actually one of probably the simplest kind of an arrival process. The Poisson point process literally has 2 properties you need to describe it. The first property is that the probability that an arrival occurs in a tiny little time step, delta t, is equal to the rate of the arrival process at that time, tau, here's lambda of tau, times the size of the time increment delta t. Sounds very obvious, right? So lambda is the rate times the arrivals per second times the seconds gives you the probability with which there will be an arrival in this tiny little time step. But what makes it special is that probabilities of arrival in any 2 disjoint time intervals are statistically independent random variables. So the way you could program your computer to generate such a random Poisson point process is you just go through tiny little increments of time from say 0 to say 10 seconds, for example, if you want. And then from each of those tiny little segments of time, you toss a coin with probability p, you generate a click or an arrival, probability 1 minus p, you see no arrivals. And then that gives you an instance of a Poisson point process in the limit of delta t going to 0. So let's take a Poisson point process with a constant arrival rate. So lambda of t doesn't change, it just says constant. And we will look at what is the probability distribution of when the first arrival occurs. So I'm starting to look at the Poisson point process at time t equal to 0. And I'm going to ask, at what point in time will my first click or first arrival occur? And I'm going to denote that by a random variable, this cap tau. And we'll be interested in deriving the probability distribution of that first arrival. And obviously, since it's a probability distribution, this thing has to integrate to 1 from tau going from 0 to infinity. Okay, so that's let's try to work on that, and then we will then solve another question, finding the probability distribution of the total number of arrivals within a time window 0 to capital T. So let's first attempt the first question. What is the probability distribution of the time of the first arrival? So the way I'm going to approach this problem is we'll take this time interval from 0 to capital T, and I'm going to chop it up into these tiny segments, so delta T long. And this red cross denotes my first arrival. And, so no arrival happened in this bin, that bin, this bin, and so on. The first arrival happened in this time bin M. I'm going to associate this time bin index M with a time tau. So like, for example, time bin 1 is this time delta T, time bin 2 is time 2 delta T, time bin M is time tau, which is M delta T, and time bin N, the last time bin associated with cap T, the end of time over which I'm observing the process. So probability that there is one arrival in any given time delta T, I just said it is P equals to lambda delta T. Now, what is the probability that the first, let's denote by little t the time the first arrival. So what is the probability that this T is tau, the probability that the first arrival does appear here? So that probability is the probability that no arrivals occurred in the n-1 time steps prior to that time step, and an arrival did occur at that mth time step. So 1 minus p to the n-1 times p. Now I can go ahead and substitute the values of p here in terms of lambda delta t. But instead of calculating this probability itself, I'm going to calculate the cumulative distribution function. So the probability that t is less than or equal to tau. So the cumulative distribution function, I'm just adding these numbers, these probabilities, but over this index going from 1 to m. So the probability that the first arrival occurred at tau or before, like from 0 to tau. And then I can go ahead and substitute p equals to lambda delta t, and m is tau over delta t. And if you look at this expression, you can apply the L'Hopital's rule from calculus and take delta t limit going to 0, and it's pretty easy to work out that you will get 1 minus e to the minus lambda tau. Now, we all know that a cumulative distribution function can be differentiated with respect to the variable to give us the probability distribution function. And then it's pretty easy to see if you differentiate this with respect to tau, you get lambda e to the minus lambda tau. So which is the exponential distribution. And this is another beautiful property of a Poisson point process, is that the probability distribution of the time when the first arrival happens has exponential distribution. And because the process is memoryless, meaning the arrival probabilities and the subsequent time steps are completely independent of the arrivals that happened before, this also is the probability distribution of the inter-arrival times, meaning if I if I open my eyes just after one arrival occurred and ask what is the time that I have to wait until I see the next arrival, that time also has the distribution written here. Okay, so and when I take delta t going to 0, what's really happening is that this n and m are both going to infinity, while the ratio t over tau being a constant. So n and m were just dummy variables I used to discretize this to get to an answer. It was just a means to an end, not so there is no real discretization of time. All right, so now let's calculate the probability distribution of the total number of arrivals k. Now, this is something you may already know, that if I toss a biased coin n times, where each time I have arrival with probability p, no arrival with probability 1 minus p, and then I ask how many times over those n attempts of this tossing a coin did I get a head as an answer? Did I get an arrival? So how many total arrivals did I get? So that distribution is given by what is called the binomial distribution that I've written here. So n choose k, so the number of ways k arrivals can happen in n time bins. And for each of those possible ways in which k arrivals could occur, the probability of that event is that k of the time bins arrivals happen and minus k of the time bins no arrivals happen. And now I'm going to do the same thing, take the limit as delta t going to 0 and see what is this probability distribution reduced to. So let's take perhaps 5 minutes or so and try to solve this. This is our first problem, that what is the distribution of the total number of arrivals k? I have put all the relevant formulas that you may need to solve this problem. And the answer is just when you're ready, go ahead and click on the Zoom poll. So Brianna already put the poll out. and we'll continue thereafter. And while you're working on it, if you have any questions, feel free to put them in the chat window. Christos and I are both monitoring.
I have answered a few.
You have answered a few. Okay, let me take a look.
But there are a few pending still.
Let me see. All right, let's go ahead and get started. Brianna, do you have the poll results? All right, so B has the largest, and that is the correct answer. So the B is the right answer. The distribution is a Poisson distribution. So the binomial distribution approaches the Poisson distribution when you make those time steps tiny. So that's great. Thank you so much. I'm going to answer a couple of the questions live. So one question had to do with, in all the other CQN courses, we have been talking about sending qubits. And the way you send qubits, or one way to send qubits, is you first generate entanglement between two parties, purify that entanglement using things like entanglement distillation, and then use teleportation to send qubits one at a time, using that entanglement as a resource. So you're absolutely right, Bob. On the other hand, there is another way to send qubits over a noisy channel, where you take packets of qubits and push them through encoders, which are tiny quantum computers that encode small packets of qubits, k qubits, into longer packet of n qubits. And then those n qubits get modulated in light, different ways of optical modulation of qubits, just like BPSK, on-off keying, and so forth for classical modulation. In qubits, when you send quantum data, there's GKP modulation, cat state modulation, there's single rail photonic qubits, dual rail photonic qubits, and what have you. And then it goes through the series of steps in reverse at the receiver. The former kind of quantum communication, where you send qubits via teleportation by first generating entanglement, is called two-way quantum communication. Whereas this forward error correction way of sending qubits, which more mimics how classical communication works, it's called one-way quantum communication. And one of the big tasks we are looking at in the Center for Quantum Networks is how should you architect the quantum internet? What are the resource trade-offs? In fact, someday the internet is a network of networks. A small portion of a local area network might be architected in this one-way quantum communication fashion, whereas a trunk link, say, enabled by quantum repeaters or quantum satellites, may be architected in this two-way fashion that uses entanglement and teleportation. But when a quantum data packet traverses from end to end from two users, it may have to hop around and go through these different types of networks. And that constitutes a whole research thrust on understanding how routing of entanglement, how scheduling of flows of quantum information should happen on such a future quantum internet. I hope that answers your question, but this course is not about quantum communications. The second part of your question is what part of classical communication pipeline are reused in entanglement distributions? That's a great question. As you, I'm sure, have seen in some of the previous courses, quantum communication cannot happen without classical communication as an ancillary resource. So when you add this new service of quantum communication, which is not a subject of this course, to the internet, you're going to put more burden on the classical communication service as well. So if you can improve your classical communications performance, which is the subject matter of this course, that will also assist with quantum communication, because it will eat into less of the classical communication bandwidth. All right, so let's, I'm going to leave it at that. If you have more questions about that, we can talk about it offline. So we have talked about arrivals, and one of the questions had to do with why are we talking about arrivals? Are these photon arrivals? And the answer is yes, we will be talking about photon arrivals. So let's talk about a pulse of laser light. And we will be looking at in this course quasi-monochromatic laser light. So a pulse of laser light with a center frequency omega naught, and with a tiny bandwidth centered around omega naught. So I am writing here the electric field in photon units. What I mean by photon units is that if you integrate the magnitude squared of the field over an area in the x and the y direction, and some time window 0 to t, the number you get is the mean energy, but in units of photons. And if you write that field, you will have a spatial component and a time component. This shape of the field in space and time is called a mode. And then there's an oscillatory component. I'm used to use J, although I'm not, I don't know if I've been consistent with all the slides. I'm an electrical engineer by training, and electrical engineering, they don't like to use I for the square root of -1 because I is used for current, but J is just square root of -1. And this phi is some phase shift. Okay, so if you look at this expression for the field, once I have identified this mode for you, there's literally just one complex number that I need to specify the state of the field. This complex number is the root of the mean photon number times this phase e to the j phi with respect to some chosen phase reference. So you have to have a phase reference to be able to talk about a phase. And this mean photon number is the magnitude squared of this complex number alpha. Now, one of the first things is that no detector can accurately measure this field, meaning I can create a field, I can work how to create a particular E of R comma T, but when you detect it, the detector must add some minimum amount of noise that we're going to talk about next. In the language of quantum mechanics, we will be using this word a lot. We will say a coherent state of a mode. So once I have defined a spatial and a temporal mode, this complex number alpha, which is the last thing I need to specify to fully specify that photon unit field, I'm going to put that inside a ket, which I'm going to specify what that means a little bit more mathematically a bit later. We will call that a coherent state. Coherent state is just the quantum state description of classical idealized laser light radiation of a mode. All right, so we'll come back to this in a little bit, but before I go forward, I do want to talk a little bit more about modes. So what is a mode? And as I said, a mode is just this as a bucket. It's a shape of your electric field in space and time. And there are 3 degrees of freedom in defining a mode. There's space, there's time, there's polarization. So this is a function, a mode function. This nu can take 2 values, 1 or 2, based on if you have circularly or anti-circularly polarized light, for example. Then there's the spatial component and temporal component. Now, I will always make sure that my mode functions are properly normalized. So meaning the magnitude squared of the mode function integrates to 1 over the area and time that you are defining that mode function over. Okay. And I will also say that 2 modes are orthogonal. This phi nu RT and psi mu RT are orthogonal if this overlap integral among those 2 mode functions is 0. And now when 2 modes are orthogonal, what it means physically is that there exists a physical device that can separate the content of the field in those 2 modes. So for example, if I have a field that is it can be written as A1 phi 1 of t plus A2 phi 2 of t, there exists a device that will separate out A1 phi 1 of t and A2 phi 2 of t, even if phi 1 and phi 2 were temporally overlapping temporal modes. Now, when we ask the question that if I give you some time window and a spectral bandwidth, what is the number of modes that you can fit in that time bandwidth product that are orthogonal to each other? So this is, I'm just rewriting Fourier transform and Fourier inverse, which you're familiar with, I'm guessing. So if you let's say ask the question that I want you to write mode functions phi k of t, such that these mode functions are orthogonal to one another. But I also want you to make sure that these mode functions are roughly confined to this 0 to t time window, and their Fourier transforms are roughly confined to this W hertz bandwidth window. What's the maximum number of such mode functions that you can fit into that window? The answer is given by roughly the product of W and T. This answer actually came through this beautiful paper from 1960s by David Slepian, who wrote down what those optimum mode functions are. They're called prolate spheroidal mode functions. And all of this above obviously holds for spatial modes as well. Now, if you look at, just to develop some intuition about the choice of these WT modes. So if you take the time 0 to t and take a little time window tau, and let's say you define mode functions, and I should have written here, so that the height of these mode functions is is 1 over square root of tau. So what's happening here? I'm sorry about this. All right, so these green functions, they are mode functions that are orthogonal to each other by design, because if I multiply these 2, I won't even have to integrate to get 0. The product itself is 0. So these are orthogonal modes. But each of these modes, their bandwidth is roughly 1 over tau, right? So, so if I multiply the 1 over, multiply the bandwidth with T, capital T, that is the number of little modes that I can pack in. So this is the most intuitive way to think about the time bandwidth product. But look at these modes. This mode function spans the entire time window, and that mode function also spans the entire time window. These two are orthogonal to each other. And same as this one and this one. And these mode functions that I've written here, there's also the WT of these mode functions. And if you have a Verizon phone that uses the CDMA standard for communication, that's most likely using these mode functions to multiplex different users on the same channel. So they're these called CDMA chip waveforms. Okay, so let's talk about that flat top temporal mode that I showed in the previous slide, that mode right here. 0 to t, and it's 1 over square root of t, so that it integrates the squared phi of t integrates to 1. And now when I say I want to excite this mode in a coherent state, as I said, all I have to specify is that complex number. The complex number is nothing but that a times e to the j theta. So this a is the square root of n, the mean photon number, and theta is that phase. So I'm going to put this coherent state in this phase space, or real and imaginary space. And Christos is going to go into quantum representations of light, of non-classical light in that phase space. We'll get a little more complicated. Right now, all I'm doing here is just putting a little dot on the complex space. Well, so this is the field of this laser light pulse, or coherent state of this flat top mode. And now, if I do photon detection on this coherent state, so it goes to one of the questions that was asked, what happens is you get a Poisson point process. These red crosses are the arrival instance. And the Poisson point process has a rate which is equal to the magnitude squared of the photon unit field. So in this case, the magnitude squared of the photon unit field, this S of t, is nothing but this constant lambda. So lambda, which is the photon arrival rate, E squared, times the t, total pulse duration, the mode duration, is the mean photon number in the pulse. So again, when I say a pulse, I'm talking about a coherent state of the mode, which is a laser pulse that comes out of your laser source. And a mode is just an abstract concept. It's a unitless bucket. It's a shape of the field that you excite in this coherent state. All right, so these are the time steps where the arrivals happen. And as I had proven earlier, the probability distribution of the first arrival has this exponential distribution, and the probability distribution of the total number of clicks that happen. So notice that I'm using the word arrival and click interchangeably. And from now on, I'm going to switch to using clicks, because we will be talking about photon arrivals, which literally are clicks. If you have a good high quality single photon detector in your lab, you feed it with a weak coherent state, a laser light pulse, you will see the detector go off at discrete time steps. And those are these clicks, tau 1, tau 2, tau 3, and so on. Of course, any real detector in the lab will never generate a true Poisson point process. It will sometimes generate clicks even when there is no light. Those are called dark clicks, and you will not be bothered by those right now. Schematically, this is what Christos and I are both going to use to show detection. This is a detector. And for this course, we'll always be concerned with this idealized detector meaning which is driven by this Poisson point process. Some of you may have heard the word shot noise. So this is also called shot noise in the context of classical optics. And a coherent state alpha is detected by that detector, and you get a number k, which is the total number of clicks at the after detection. Okay, so let's do a little bit of problem solving with what we have learned already. So one of the most common formats in which information is modulated in traditional laser communications systems, most likely the Comcast or Cox fiber that is bringing internet to your home, that uses this on-off keying modulation. It's very, very simple. That, remember when I talked about after error correction, you get this stream of zeros and ones that need to be modulated in your laser light. Let's say I modulate the 0 by not sending any light, and modulate the 1 by just sending a laser pulse with some mean photon number n. Okay, so that's on-off keying. So this is hypothesis 1, this is hypothesis 2. And let's say n is the mean photon number in that laser light pulse at the receiver. So after it has gone through attenuation in the fiber, this is the pulse I've received. And my job is to tell apart between whether I got hypothesis 1 or hypothesis 2. Let's assume that both hypotheses occur with equal probability, so their priors are 1/2. Now, if you were to detect light using an ideal detector, it's very obvious what you're going to do, right? You wait for the first click to occur. The moment you get a click, you raise your hand and say, I got hypothesis 2. There's no way you could have gotten a click in hypothesis 1.
Sorry, Saikat, there is a question that might need to be answered now.
Sure.
Someone asks, what is the difference between big K and little k?
Oh, very good point. In all of my notation, I'm using capital letters for random variables and lowercase letters for instances of the random variable. So little k is a random number and capital K is the random variable. So the way to read that notation here is that this is the probability that my random variable capital K takes the value little k is equal to e to the minus n to the k over k factorial, where little k can be 0, 1, 2, 3, 4 up to infinity. So if you add up these numbers over little k from 0, 1, 2, 3, 4 up to infinity, you get 1. So that's the notation also being used for continuous random variables. Anything else that I should answer now?
Not really.
Okay, thanks. So as I said here, you just wait for the first click suffices. So now the question is, what is the probability that you'll make an error in telling apart between hypothesis 1 and hypothesis 2, even when you have this ideal detector? So well, Bayes rule. So you all have probability as a prerequisite for this course. So probability of an error is the probability that hypothesis 1 was indeed true times that you made an error plus the probability that hypothesis 2 was true times that you made an error. And when I say you made an error, this notation means the probability that your receiver guessed hypothesis 1 given that hypothesis 2 was true. And same here. Well, so let's look at this first part. What is the probability that you will guess hypothesis 2 given hypothesis 1 is true? If hypothesis 1 is true, the only way you can make an error is if a click occurs, right? If k, the number of photons you get, is greater than 0. Now, can you tell me what this is? This is not going to happen. This probability is 0. You're never going to get a click if hypothesis 1 is true. So this first term is 0. But if you look at the second term, what is the probability that you will guess hypothesis 1 if hypothesis 2 is indeed true? So this second term is the probability that you have a pulse, okay, but you still did not get a click. What is that probability? The probability that you get 0 clicks is e to the minus n to the 0 over 0 factorial, which is nothing but e to the minus n. So with probability 1/2 that hypothesis 2 is really true, the conditional probability that you make an error is e to the minus n. So the overall average probability of error is 1/2 e to the minus n. So no matter how good your detector is, you are going to have at least this much error probability, and it would very likely will be more. So this is some people call it the short noise limit in the context of classical light. Okay, so let's talk about the next modulation format, the binary phase shift keying. Now, a binary phase shift keying modulation format, again, it's a binary format, meaning there are two modulation levels, but instead of an off and an on, meaning not sending light or sending light with some mean photon number, this time we are always going to send some light. So you get the stream of zeros and ones at the output of your error correction encoder. I'm going to modulate the zeros with a laser pulse with mean photon number n, and modulate the ones with another laser pulse with the same mean photon number but with an opposite phase. So remember when I said that there's a complex number has an amplitude and a phase, this phi is the one I'm changing from 0 to pi. So what if you were to physically look at that pulse if you could precisely look at the actual electric field, what you will notice is that the oscillatory portion of the field, which oscillates at the center frequency of omega naught, which I'm not writing on this slide, there's a pi phase shift in that oscillatory component. But we don't have to worry about the oscillatory component because as we talked about, we can just look at the complex numbers alpha and minus alpha, and that's what we are. Oh, I'm sorry, my mouse is doing weird things. Okay, so alpha and minus alpha, this is what we want to tell apart. Now, the first thing you notice here is that how am I going to be able to tell apart between them? If I just use a detector, if I use photon detection, it will generate the same Poisson point process, because the photon detector's output has nothing to do with the phase. It doesn't care about the phase. The rate of the Poisson arrival process lambda is nothing but magnitude squared of E times e to the j5, which is always E squared, which is n over t. That's your lambda. So photon detection is a useless detector to tell apart between VPSK signals. So let's take a pause here, and we'll come back to this question, but to develop some intuition as to how we might design receivers that can tell apart between VPSK signals, let's go and talk about interference. And this will be our second physics concept that we are going to learn about in module 1. The first concept was Poisson point process and photo detection, and the second one will be interference in passive linear optics, or something that is known as a beam splitter. Beam splitter it actually looks like it's a piece of glass. It looks like a cube in the lab, and you can shine light from two directions. You can put two laser light pulses, two coherent states, one with an amplitude alpha 1, another with an amplitude alpha 2. And when they meet on that beam splitter, which is defined by a transmissivity eta, the outputs of the beam splitter, again, two output faces or facets of that piece of glass, you get two laser light pulses that are in a product state in the language of quantum mechanics, which you know, meaning the state of the when two outputs are independent with each other. You can write it as a tensor product. And not only that, both of those are also coherent states. And the amplitude of those two coherent states, beta 1 and beta 2, can be written like this column vector, which is a complex valued 2 by 2 unitary matrix multiplying this column vector alpha 1, alpha 2. So there are only two parameters that I need to specify a beam splitter. This theta and phi, where theta is related to the transmissivity of the beam splitter. Why do we call it the transmissivity? Well, because if eta was 1, then what will happen is that beta 1 will be equal to alpha 1. So the light just goes through this way, and alpha 2 just goes through that way. Alpha 2 equals to beta 2 equals to alpha 2. All right, so this beta, I'm going to write this bold-faced beta as the column vector, use the unitary, alpha as the column vector. So let's do some examples of beam splitters. And by the way, what you will see in Christos's portion of the module 2 is that this property, that a beam splitter mixing two light pulses, generating a tensor product of two light pulses at the output, is a unique thing that only happens when those modes, the input of that beam splitter, are excited in coherent states. And this kind of interference is what we are also seeing in sound waves. Well, for that matter, when you throw a pebble in a pond and you see two ripples that are interfering with each other and forming this beautiful interference pattern, that kind of interference is no different than this kind of interference we are talking about, where two laser light pulses interfere on a beam splitter. But then when Christos describes to you how two single photon states, when you excite the modes in single photons or squeeze states of light, these are non-classical states of light, when they meet on a beam splitter, that interference is nothing like interference of sound waves, or those interference of those ripples of water. That's a different kind of interference to understand, which we need to develop more mathematics of quantum optics. Okay, let's get to that later. Let's look at this coherent state meeting on a beam splitter and we'll do some examples. My convention is always going to be this: beta, the first output, is square root of eta times alpha 1 plus square root of 1 minus eta times alpha 2 with a phase, and beta 2 is this expression here. So if you look at alpha and minus alpha, if this is what I interfere on the beam splitter, on one output, you get alpha plus minus alpha over root 2, because eta is square root of 1 over 2. Eta is a number between 0 and 1. So you get no light here, you get 0, you get a vacuum. And the other one is alpha minus alpha, which is 2 alpha, divided by square root of 2. So that's square root of 2 alpha. So all the light appears here, and this output doesn't get any light. This is called, well, depending upon whether you're looking at this output port or that output port, it is destructive interference or constructive interference. And again, this is just like, as I said, this is like how ripples of waves on a surface of water or sound waves interfere. Pure phase. Well, if I set eta to 0, it is nothing but it's a reflector. It's not a beam splitter anymore. So this light gets reflected, goes out this way, beta goes out this way, maybe gets a phase. So it's a special case of this unitary. And one other fun use of the beam splitter is to do nulling, which is a slightly non-standard way of using a beam splitter, but it's easy to work it out. So let's say that I put the first input in alpha. The second input, the amplitude I choose to be beta over square root of 1 minus eta. Note that I'm choosing this amplitude as a function of the eta, the transmissivity itself. And let's say I have bought a beam splitter with a transmissivity of 0.99. Very, very highly transmissive beam splitter. So if you go ahead and put it back in this formula, and I take phi to be 0. So take a look at beta 1. This is the beta 1 output, let's say. Okay. So square root of eta is almost 1. So I'm going to ignore this. Alpha 1, which is alpha. So I get the first term is alpha, plus e to the I phi is 1, because phi is 0. Square root of 1 minus eta times alpha 2. This is alpha 2. So square root of 1 minus eta cancels out. So I get beta. So I get alpha plus beta. So with this arrangement of having a highly transmissive beam splitter and a very strong local oscillator. Why is it strong? Because if eta is very close to 1, 1 minus eta is very small, which is in a denominator. So beta over square root of 1 minus eta, it has a very strong laser pulse. So with a strong local oscillator and a highly transmissive beam splitter, I was able to turn this interference into a gadget that can add two complex numbers. I can take alpha to alpha plus beta. So this is in the language of quantum optics. It's called displacement, or you can also call it nulling in a more conventional interferometric language. All right, so now that we have talked about a beam splitter, let's talk about how can you generate this 2x2 unitary, 2x2, this general beam splitter unitary by two 50-50 beam splitters, meaning eta equals to 1/2 with no phase, and two pure phases, phi and 2 theta. I'm not going to do the math, but you can work out the math yourself. You can take alpha 1, alpha 2 as a column vector, first multiply alpha 1 by a pure phase. So you get alpha 1 times e to the I phi here, then take that and alpha 2, put it through a 50-50 beam splitter, again, multiply the top arm's amplitude by e to the I 2 theta, go through this process again, beam splitter. What you will get is beta 1, beta 2 will be given by this expression here. So lesson learned is that I can generate a general 2x2 beam splitter by having two beam splitters with static 50-50 beam splitter, no phases, and two phases that I can modulate, theta and phi. This thing is known as a Mach-Zehnder interferometer, and I'm going to denote it by this little symbol, alpha 1, alpha 2 here, alpha beta 1 and beta 2 here. And this is the unitary that it implements. Now you can ask the question that, well, what if I wanted an n-port interferometer? I have n input modes and n output modes, and I have a column vector of beta, these amplitudes, and use an n by n complex valued unitary matrix. Okay, so one can show that in a general n-port interferometer can be decomposed in this way, where each of these tiny crosses that you're seeing here is a Mach-Zehnder interferometer, which, as you remember, has two unspecified phases and two 50-50 beam splitters. So, and how many beam splitters do you need? Well, you need n times n minus 1 over 2 Mach-Zehnder interferometers. But you know that each of these Mach-Zehnder interferometers is two beam splitters in two phases. So at the end of the day, if you can design a chip that has n times n minus 1 divided by 2 times 2, which means n times n minus 1 tunable optical phases, which you could tune, for example, applying local heat to modulate the refractive index right at that point of light in the chip, or electro-optically modulate the phases. You can design a gadget that can implement an arbitrary unitary transformation U on n modes in a fully programmable fashion. So my colleague, Professor Dirk England, who is also, he's at MIT, and he's also the deputy director for the Center for Quantum Networks. Dirk's group specializes in building these very large programmable linear optical circuits, like the kind I'm showing here, which he uses, for example, for not just interfering in classical and quantum light, but to do all optical computing, for example, for machine learning enabled computations on optically encoded information. Okay, so with that, let's go back to our on-off keying example and ask ourselves that instead of detecting photons, what if I first displaced my signal before I detected it? I'm sorry. So let's say I'm given with 0 or alpha, but I'm not detecting it right away. So I first take my signal. This input signal is where I'm putting my input in, 0 or alpha. This goes in here. So gamma is just a dummy variable for either 0 or alpha. In the output, I'm getting either beta or alpha plus beta. And then I detect that pulse. So pictorially, this is how it's going to look like. So even the off signal is going to now get some light. The on signal is going to get brighter. Okay, well, so you can do the math. The error probability now will no longer be 0 if you have hypothesis 1. Why? Because if you detect, you have a probability that you will get a click. And if you get a click, if your decision rule still is that if I get a click, choose hypothesis 2. If I don't get a click, choose hypothesis 1. There will now be a probability of error that will appear even if hypothesis 1 is true. Why? Because if hypothesis 1 is true, which is this hypothesis, you will make an error if a click does appear. And the probability that at least one click appears is 1 minus the probability that no click appears, which is e to the minus beta squared. So this is going to get, this term is hurting us. But then this term helps us. Why? Because the probability of error when hypothesis 2 is true, it lowers because the probability of error is you get no clicks if this hypothesis is true, which is now going to become a smaller number because it's going to be e to the minus alpha plus beta whole squared instead of just e to the minus alpha squared. Now, funnily enough, if you take this expression and optimize over beta and plot this probability of error as a function of n, the mean photon number in the on pulse, you get a performance given by this blue dashed line, which is much better than the probability of error we got with direct detection, which is what we all use in conventional laser comm systems. Use on-off keying and a Poisson short noise limited linear mode photodiode, photon detector. That's all. So just by using this interference, this very, very simple thing, this beam splitter with a local oscillator, prior to subjecting that information bearing light to that inevitable detection noise, you were able to reduce, you were able to improve an information metric like an error probability. And this lies, this theme underlies almost all my research, all of the things that we do in our group, that doing something to the optical field prior to detecting it, and that thing in this case was just a beam splitter, but that thing in the optical domain could involve things like squeezing, interference, nonlinear optical interactions, and so forth, can position that information bearing light in a more favorable way to that detection noise that is yet to come. All right, so now you can ask the question, well, you showed me one receiver design that can beat direct detection. What is the best possible or minimum possible probability of error that is allowed by the laws of quantum mechanics? Now that answer, I'm going to show you how to derive that in a bit, but I'm already plotting that answer here. This is called the Hellstrom limit. And this is, as you can see, it's a little better than this simple receiver. And this simple receiver has a name. It's called the Kennedy receiver because it was invented by a person called Robert Kennedy in his MIT RLE progress report in 1972. And Kennedy's student, Sam Dolinar, who is now, he's been at the Jet Propulsion Laboratory all his career. He works in error correction codes for space-based communications. He, in his PhD thesis in 1973, invented a receiver design that achieves this minimum probability of error, which I'll talk to you about in a second. Okay, so now we are ready to go back to BPSK, which we had shelved because we did not know how to tell apart between BPSK signals, alpha and minus alpha. Because if you did photon detection, there's no way you can tell them apart. But now that we are armed with this additional thing we could do to the light pulse before I detect it, I could displace the coherent states, minus alpha and alpha to beta and 2 alpha plus beta. Or even choose beta to be equal to alpha, in which case minus alpha will go to 0 and alpha will be moved to 2 alpha. And then do photon detection. And if I do that, I get a probability of error. And if I choose beta to be 0, which is the receiver design that Kennedy actually proposed in 1972. And then Masahiro Takioka and Masahide Sasaki in 2008, they found that, well, beta equal to 0 is not optimum. You can get a little bit better probability of error by optimally choosing beta. And I'll show you the plot for this error probability later on. Now, one of the things with this receiver, the Kennedy receiver, is that you need this local oscillator, this to shift minus alpha to beta, which has to know alpha a priori, right? Which is kind of a not so desirable, right? When I'm receiving some laser-like pulses, if your receiver needs to know the amplitude of the pulse before, in order for it to do that optical processing. You have an estimate of that, but can we design a receiver, interferometric receiver for BPSK that doesn't need to know that amplitude reference? Well, so that's where homodyne detection comes in. So homodyne detection actually just uses an interference and Poisson short noise limited photon detectors. So here's how it works. Now, this is my laser pulse that I want to detect using homodyne detection. And I interfere that with another laser light pulse with an amplitude alpha LO. On one output, I get alpha plus alpha LO over root 2, and another output, I get alpha minus alpha LO over root 2. So it's a 50-50 beam splitter. I detect both of these using 2 photon detectors. Okay, and I get 2 photocurrents, which are this photocurrent is that Poisson point process, remember, of that is generated by this detector. There's another Poisson point process generated by this detector, whose Poisson point, this amplitude is driven by the rate is driven by this amplitude. And then I take a difference of these 2 photocurrents and integrate that over the pulse duration, and maybe multiply that by some scale factor S, and I get a number Y. Now this Y is a random variable we are going to try to find the distribution of. Well, this Y can be written as follows. So I can think of this Y as the difference of 2 Poisson random variables, K plus and K minus, times a scale factor. And the scale factor is the product of the electronic charge, which is the area of that one delta function that appears when you detect a photon, times this gain G, times this additional scale factor S that I multiplied. Now, since I chose alpha LO to be very large, but this is a strong local oscillator, both n plus and n minus, the mean of these 2 Poisson random variables is extremely large. And when a mean of a Poisson variable is very large, it approaches a Gaussian random variable. And you probably, as you know, the Poisson random variable has the same mean and the variance. So lambda is the mean and lambda is also the variance. So it approaches a Gaussian distribution or a normal distribution with a mean and the variance being the same. They're both lambda. Well, so I get a random variable Y, which is a Gaussian, because the subtraction of 2 Gaussian random variables is also a Gaussian. So this is a Gaussian, that's a Gaussian. So I get a Gaussian random variable whose mean is a subtraction of the means of the 2. And the variance of this random variable is a sum of the variances of the 2. So I get this as the mean, and that as the variance. So now what we are going to try to do is, so by the way, this thing is called a balance detector, which you can buy from Thor Labs, for example, or Newport. So if I take this mean and the variance, okay, mu and sigma squared, we can choose this S however way we want. Okay, we can choose the scale factor. This is in our hands. So let's pick this scaling constant S such that the mean mu equals to alpha. So if you want this to be alpha, you'll have to pick S to be equal to 1 over 2QS alpha LO. So let's try to do that. Let's try to pick S to be equal to that and take the limit of alpha LO going to infinity, or being very large in comparison to the alpha. And let's see if you can find out the distribution of Y. I'll just give you a couple of minutes here to work it out. It's a very simple problem. And it will be obviously a Gaussian. And the mean is obviously alpha because I designed it to be so. I chose my S so that the mean is alpha. I just want you to calculate what the variance of this random variable will be. Okay, so I have answered most of the questions in the chat window. Let's go ahead and show the results, Brianna. Great. So we got again most of the answers are right. It's so it is indeed A. So the variance is 1/4, and that 1/4 variance is an unavoidable noise variance for homodyne detection, even if you have idealized photon detectors. So that's called the shot noise, not shock noise. I'm sorry if I said that, or at least appear to have said that. Somebody for homodyne detection. Somebody asked a question about state of the art for this crossbar switch. I don't remember. I think Dirk's group has built. I know for sure that he has a 12 mode input, a 12 by 12 fully programmable nanophotonic processor, at least a research grade one that they're using. His group also spun out a company called Light Matter, and they use these all optical crossbar photonic integrated circuit switches for machine learning. And I know that they're routinely using 8 mode circuits, but I'm sorry, I don't know what the state of the art is. The other groups would be Jeremy O'Brien, who has done a lot of work in Bristol before he went to PsiQuantum to look at. So I would say I plan to have a little break here, but we took a little break anyway in solving the questions. So I suggest that we keep moving forward. Let's see how we are doing with time. So we are at 1 hour, 25 minutes. So I think we are 3.5 hours. Let's say I take 15 more minutes, and I think we'll be at roughly at the half point. Is that okay?
Yeah.
All right. Okay.
Also, I think my slides will not take that much. So we're gonna have a small break after you're done.
Okay. Sounds
We
good.
have like reserved up to noon.
I see. Okay. I think we should be good. All right. So let's keep moving forward. So now we talked about homodyne detection. Now in homodyne detection, then one nice thing is that this local oscillator alpha LO could have a phase that you could choose. It doesn't have to be in phase with your input. So I can choose this theta LO to be different than my input, the phase of my input signal. And if you did the math, what you will see is that you will still get this 1/4, but the amplitude, instead of being alpha, it will be alpha times e to the j theta LO, which means that you get to choose which quadrature of the input signal that you are measuring. Meaning, if you set theta LO to 0, you are measuring this square root of n cosine theta is your mean field, and the variance is 1/4. But I could choose my theta LO so that instead of measuring this, I'm measuring that, right? I can measure the imaginary component, or for that matter, I can rotate the real imaginary axis in, say, some ways that the real axis is like that. I can measure this component, the projection of this complex number on some tilted axis. So this is the cool thing about homodyne detection. You get to measure any phase any quadrature that you desire. Now that we have learned homodyne detection, you can see how you can use this to decode BPSK signals or detect BPSK signals. So if I have minus alpha or alpha, if you do homodyne detection, you're going to get 2 Gaussian random variables with a mean of minus alpha or alpha. But in both cases, the variance is 1/4. So you have 2 Gaussians with different means, same variance. Your maximum likelihood detection rules should say that if your that output y is less than 0, you guess it to minus alpha. If it's greater than 0, you guess it to be plus alpha. And you will make an error, which is given by the integral of this tail of this Gaussian. If you work it out, you get this ERFC function. So 1/2 times ERFC of square root of 2n bar. So n is the mean photon number of this coherent state alpha. Okay, so there is another way to detect signals which is very popular in quantum optics, and I'll tell you about why this is interesting. Unambiguous detection. Unambiguous detection is when you desire your receiver to, when it does declare a hypothesis to be true, you don't want it to make an error. But you allow the receiver to sometimes declare that I don't know. Just sometimes just fail and say that, I don't want to make a guess. But when it does make a guess, you want it to make a right guess. So let's see how you can design a very, very simple unambiguous detection for BPSK. So let's say I know my amplitude alpha or minus alpha, which I'm going to put into this port of this first beam splitter. I pre-prepare the first input to be in a state alpha. So so now if hypothesis 1 is true, if alpha is the one that goes into this port, the output here will be alpha plus alpha over square root of 2, which is square root of 2 alpha, and this output port will be 0. But if you put minus alpha into this port, you get alpha plus minus alpha over root 2, which is 0. And this port will get alpha minus minus alpha over root 2, which is square root of 2 alpha. So you'll get constructive or destructive interference depending upon whether you put alpha or minus alpha into the second port of the beam splitter. And let's say I have detectors on both of these outputs. Now, if this detector clicks, generates one or more clicks, you have to have had the blue hypothesis. There is no way the red hypothesis would have generated a click because there is no light here. Okay, and so if my input x, and x equal to 1 and 2, I'm just denoting the my input to be alpha minus alpha. If x is 1, if your detector happens to generate a click, which happens with the probability 1 minus the detector not generating a click, which is probability is e to the minus magnitude squared of this quantity, which is 2 times alpha squared, 2 times n. But you never make a wrong guess, because if your detector does not generate a click, you just say that, I don't know. But with probability e to the minus 2n, in both cases, you just make this erasure guess. This y equals to 3 is the output that says that I don't know. Such a receiver is called unambiguous state detection. Now, if you force your unambiguous state detection receiver to finally make a guess, which is just not designed for, then if it gets an erasure, it can just make a random answer. It can just say that, oh, it was hypothesis 1. And then obviously it will make an error with probability v minus 2n. Unambiguous state discrimination for more than 2 coherent, more than 2 inputs is a very interesting open problem, and it has applications in designing receivers for communications, especially when you are designing receivers that act collectively on a code word that is comprised of many pulses. I'll come back to this in a second. I did want to mention heterodyne detection. Somebody mentioned that in the chat window. This is a common format that is used in FiberComm's high order modulation formats like QM, QPSK, and other modulation formats. Heterodyne receiver is very popular. You can think of heterodyne mathematically, although this is not how it is done in the lab. You can think of heterodyne as splitting the input into 2 outputs through a beam splitter with vacuum going into the other outputs. So you get alpha gets split into alpha over square root of 2 and another copy of alpha over square root of 2. And you just do 2 homodyne detections on these 2 copies, but with a phase theta LO equals set to 0 or set to pi by 2. So what happens is that complex number alpha, you measure both the real and the imaginary component. Now, of course, you get these 2 outputs with the 1 over 4 variance. But if you scale the 2 outputs such that the mean of the Gaussian random variable is actually the amplitude alpha, its real component or its imaginary component, then the variance becomes 1/2. Because of this square root of 2, you have to multiply this with, so you have to multiply the variance by 2. So this 1 over 4 becomes 1 over 2. So the lesson learned is that when you do heterodyne detection, you get to measure 2 quadratures simultaneously, but the price you pay is that you have twice as much noise in each of the outputs. But if you have something like a QPSK modulation like that, you cannot decode this by homodyne detection, because homodyne detection will only measure 1 quadrature. But heterodyne is perfect for this because you can measure both the real and imaginary component. And QPSK modulation is where you take 2 bits of your encoded signal at the output of your error correction encoder at a time, and for each of these 2 bits, you pick one of these 4 states of the laser light pulse in one time bin. So if you plot the error probabilities of your BPSK signal, what you see is that this red line is the performance of homodyne, this blue line is the performance of the Kennedy receiver, this pink line is the performance of this USD receiver, but forced to make a hard decision. And this black line is something I haven't told you how to derive, which we are going to talk about next, the optimal receiver, which is achieved by the $1 receiver. All right, and there's a difference between how these scale with mean photon number n as n increases. But in order for me to describe to you this minimum error probability, I'll have to describe to you a little bit more about some machinery of quantum mechanics, which I'm assuming that you have because of the prerequisites of the course, but we are still going to go over some notation quickly. A quantum state, a pure state, is described by a unit norm column vector psi. A measurement is described by a set of unit norm orthonormal vectors, WK. If a state is measured by this measurement, the outcome K happens with probability that is given by the magnitude squared of the inner product between the state psi and the kth measurement vector. So if two states psi1 and psi2 are orthogonal already, I can choose my measurement vectors to be W1 and W2 be equal to the psi1 and psi2, right? Because they will be orthogonal. So that's my condition for a one-dimensional projective measurement. And it will achieve a probability of error of 0. Why so? Because if psi1 is the state that I have been given, the probability that I will get outcome 1 is 1, and probability that I get outcome 2 is 0. So I will never make an error. Conversely, if two states are not orthogonal, then I cannot find a receiver, a measurement that can tell them apart with probability of error of 0. Christos is going to talk about different states of light. I'm going to introduce just one state of light in an intuitive fashion. So I talked about a mode and exciting that mode in a coherent state. And if I do ideal photon detection, you get a Poisson random variable of mean n is magnitude alpha squared being the total number of clicks, total number of photon detections that you get. What if I was able to excite that same mode phi t in a state that I call a Fock state that has a perfectly fixed number of photons n? Now, you could generate a state like that, although it is very, very hard to generate it experimentally. People generate routinely states where n equals to 1. It's called a single photon state. But now if you notice the state of light, if you detect a pulse excited in a mode excited in state 1 in a photon detector, you will still get one click randomly during the course of that mode. Where that happens will be random, but then you will get one click. You will never get 0 clicks. You will never get 2 clicks. You will always get 1 click. So it's a highly non-classical state of light. But one thing that you immediately realize is that if you take these Fock states, there are infinitely many of states of this mode phi t. But if you take this Fock state, and if you do ideal photon detection, then you can tell them apart with 0 probability of error, right? Because you'll just get the number of clicks will match the state that you had. And I just told you that if a measurement exists that can tell apart between two states, then those states must be orthogonal. So the Fock states are orthogonal to one another. And Fock states, n has an energy of n photons. So since n can go from 0 to infinity, they span all the energy and they form an orthonormal basis. So any quantum state of light, any pure state of a single mode can be written as a superposition of these Fock states because they form a basis. So you can, because they're a basis, I can think of these Fock states as infinitely long column vectors that are orthonormal to one another. And in this language, a coherent state can be written as a superposition of these Fock states, where the coefficients are square roots of Poisson distribution. So that when I make a measurement, an ideal photon detection, which is simply a one-dimensional projective measurement described by these vectors n. So these are your W's, the measurement vectors. You get the Poisson distribution because the probability of getting the nth outcome is the inner product magnitude squared of alpha with n, which is this Poisson distribution that we saw earlier. Now, with this language, when I have written the coherent state as a superposition of these Fock states, I can take an inner product between two coherent states, and that number is never 0. So no two coherent states have a 0 inner product, meaning no two states of light, laser light, can be told apart with any receiver with 0 probability of error. Of course, to Dan Kilper's point, when alpha is large, of course, this inner product becomes very close to 0. So we don't care but we do care when alpha is very small and this inner product can be significantly away from 0. All right. So Poisson detection statistics on laser pulses is a result of the projection of the quantum state, which is a coherent state of the laser light of the mode, onto one of the Fock states. Well, so in general, in quantum optics, we talk about a set of modes and then talk about the quantum state of those state of modes. So that's the complete description of an optical field. You cannot write a field in quantum optics. You have to identify a set of orthogonal modes that you care about and write down the quantum state of those modes. The most general pure state of a mode, as I said, is a superposition of Fock states. Ideal direct detection is the measurement vectors are these number states. There are examples of pure states for mode. I talked about coherent state, Fock state, But I can take two coherent states and write a summation of them, alpha plus minus alpha or alpha minus minus alpha. Okay, I have to pick a normalization constant, obviously, so that the status has a proper normalization. But these states are called cat states. They're a highly, highly non-classical state of light. It's like a superposition of a mode being plus alpha or minus alpha. This is not a coherent state anymore. And how do you see that? Well, it's very easy. Write down the photon number expansion of this cat state, the even cat state and the odd cat state. The reason they're called even cat state and odd cat state is when you write this cat state number expansion or Fock state expansion, you only get even numbers. So if I were to photon detect this cat state, I will never get 3 clicks. I will only get 0, 2, 4, 6, and so on. Similarly, for odd cat states, I will only get an odd number of clicks. And again, you should observe here, because I have a detector that can tell apart between these two states with 0 probability of error, the inner product between these two states should be 0. And the moment I have two states, whose inner product is 0, they are orthogonal states, I can encode a qubit in those two states. So cat states, for that's reason, is one of the popular methods to encode a qubit for people who do continuous variable photonic quantum computing. And there's a company called Xanadu that is working on quantum computing by encoding qubits in 2 states of light. And they don't use cat states, but they use another state of light called GKP states, which we will not get into in this course. You already have heard about entangled states. Entanglement is where you cannot write the state of, say, 2 modes in a product state form, like the state of the first mode and the state of the second mode. And for example, a general state of 2 modes, which is a superposition of the first mode being in the Fock state N1 and the second mode being state in Fock state N2. Most of these states do not factor into the state of 2 modes. And one of the examples that happen a lot in quantum optics is the noon state of 2 modes, where either the first mode has n photons and the second mode is vacuum, or vice versa. And these noon states are a good resource for phase estimation. All right, so now we are ready to tell you the last part of the story on how you can write down the quantum limit of the minimum probability of error. So let's solve the very simple problem of psi1 and psi2, 2 states that are not orthogonal. Because if they're orthogonal, then you know already that the minimum probability of error is 0, and you know how to design the measurement. The 2 measurement vectors will be the same as the state vectors. So take psi1 and psi2 inner product to be sigma. And for simplicity, let's take sigma to be a real number between 0 and 1. So psi1 and psi2 I can embed on my plane of my whiteboard. So there are 2 vectors, unit norm, some angle between them. Now, if I can just draw some x and y axis, let's say this is my x-axis, I call it 1, 0, y-axis 0, 1. And then if in this axis, psi1 will take this form, psi2 will take this form, take an inner product, you can check that the inner product between these 2 is sigma. I will just pick a measurement for you. All I need for the measurement is that this angle needs to be 90 degrees. They need to be orthogonal to each other and span the vector space in which the states live. So W1 is this vector, 1, 1, W2 is 1, -1. The probability of error is, let me take the equal priors for the 2 inputs. So probability that hypothesis 1 is true times you make an error given hypothesis 1 is true. So what is the probability of error that given hypothesis 1 is true? Well, if hypothesis 1 is true, meaning I have given you the state psi1, but by chance your measurement gave you the W2 answer, which we know is the magnitude squared of the inner product from psi1 and W2. And then the second term is 1/2 the probability hypothesis 2 is true times you make an error. So, and this measurement, by the way, happens to be the one that achieves the minimum probability of error. So I'm going to have you take just 2 minutes and calculate the formula for that minimum probability of error. So again, I have psi1 and psi2, and these are the 2 vectors that have non-zero inner product, so they are not orthogonal. And this is the measurement vector, which is 2 orthogonal states that span this state in which the states live. And I want you to calculate this, the expression. So this is actually a relatively simple problem. It's just some plug and chug. So take a couple of minutes for this, and then we'll continue on to the last part. All right, let's go ahead and show the answers. Polls, Brianna. B, excellent. So B is the answer. So you can, this is just a plug and check, you can get the answers. So by the way, so now that we know this answer, we can apply it to find the minimum probability of error for two coherent states, because we know the inner product between two coherent states. So that's how I got that black line, the minimum probability of error. Okay, so now we can ask the more general question, which I won't have the time to describe to you the math behind, but I can ask you the question that I have three coherent states or four coherent states. So like somebody, Bob Lance mentioned QAM modulation, take 16 QAM, take 16 coherent states, all those complex numbers. I can give you some prior probability of that ensemble. And now ask you, with the best possible receiver that is allowed by the laws of quantum physics, what is the minimum average probability of error that you can ever get? And that's much better than what you can get with even with ideal heterodyne detection that we use in the lab today. But how do you do the math? Now it's a much harder problem. I have these state vectors. I cannot even draw them on a 2D plane. I have to pick all these measurement vectors, WJs, such that the error probability is minimized. Now, what is my error probability? Is the 1 minus the average success probability. And the average success probability is the probability that the ith hypothesis was actually given times the probability that I made a correct decision. The probability I make a correct decision is the magnitude squared of psi I wi squared. Wi is the output corresponding to the state psi I. So Horace UN, and the same Rob Kennedy and Lax, they solved this using basically Lagrange multiplier-like tools. They found that if you define these numbers xij, which are the inner products between the states and the measurement vectors, and solve these two set of nonlinear simultaneous equations for these numbers xij's, you can find the optimum probability of error. And this third condition is what you need to check for uniqueness of the solution. So we won't be solving this, but I'll show you one example of minimum probability error detection. The main important thing I want to note here is that if I were to solve UN, Kennedy, and Lax, the YKL conditions to find the minimum probability of error for that quantum constellation, yes, I can do that right now. I can do that on the computer, perhaps, if not by hand, but I won't be able to tell you how to write even on paper a receiver design that will get you to that minimum probability of error using things I know how to build in the lab. Beam splitters, local oscillators, detectors, feedback, modulators, squeeze light. I don't know how to write the receiver design. So this is the power of quantum detection, quantum estimation, quantum information, this quantum information theory that you can find these fundamental limits even without knowing what the receiver looks like. Binary phase shift keying, we already have told you that the coherent state inner product between alpha and beta is this formula. You can just simply plug in beta equal to minus alpha. You get the inner product between alpha and minus alpha to be e to the minus 2n. And you just found the minimum probability of error formula in that last problem. So I can plug in the value of sigma and I get this formula for the minimum probability of error. On-off keying, same formula applies because these are two pure states. All you need to do is to change the sigma, the inner product between 0 and alpha. It is e to the minus n over 2. Plug it in, get the minimum probability of error. So calculation of this minimum probability of error obviously is a one line. You just solved it in the last problem. But how do we design a receiver that will achieve this? Well, for BPSK, the answer to this question, how do we design a receiver that achieves this expression? That was the subject matter of a 200-page PhD thesis of Sam Dolinar. 1973. He first wrote a quarterly progress report on the design. And he actually went with a very intuitive receiver design, which only works for two states, doesn't work for three or more, which is still an open problem. What he did was he took the input. So this is plus alpha or minus alpha. I'm just drawing the temporal shape of the pulse. And he adds it using that, that addition that I talked about earlier, alpha plus beta, using the displacement module of the beam splitter. He adds to this one or of two time varying waveforms. So u plus t or u minus t. So your actual signal is e or minus e, and you add u plus or u minus, and the receiver internally keeps a belief of which hypothesis is true. Okay, and every time your detector generates a click, and the clicks Poisson point process is obviously driven by the intensity of the magnitude squared of this sum, because that is what is fed into the detector. Every time the detector clicks, you change your mind internally about what the current hypothesis is, and you switch to applying the other waveform in this adder. and you just keep flip-flopping. And at the end of time, when the pulse is no longer there, you have gone through 0 to capital T, you just declare, the receiver just declares this current hypothesis that is holding as the final answer. And turns out by optimally choosing this U plus and U minus of T, he was able to show you can get this error probability. It's almost like magic. Okay, he was just trying this receiver design, and he knew how to calculate this formula and worked out. It was fantastic. There is one nice intuitive way to understand the Dolinar receiver. If you think about, remember I talked about these time non-overlapping temporal modes, where I can take a 0 to T and break it up into small time chunks. I can rewrite my coherent state alpha as a tensor product of k coherent states of these time temporal modes, 1, 2, 3, 4. These, I can think of these as little tiny time slices. And the minus alpha coherent state as a tensor product of coherent states minus alpha over root k, minus alpha over root k, and so on. So if I go with this interpretation that alpha, so think of this vertical direction as time. Okay, so my pulse is either this way or that way. Okay, so that's my, this is the first slice, the second slice, third slice, and fourth slice in time. And now think about how the Kennedy receiver works. The Kennedy receiver, it takes the BPSK coherent states and shifts it, applies a displacement before detection. And Kennedy was Dolinar's advisor. So the main innovation he had was that, well, I don't want to apply the same shift to all the slices. He starts the receiver with an internal belief of hypothesis 1, and he wants to use the detection outcome to prove him wrong. So he starts with the first slice and applies a huge displacement to it to the right. And now hypothesis 2, which is further away from origin, has a larger probability of generating a click. So if this slice does generate a click, which is what I'm showing with this, so there's no click that happens in this, then he just retains the current hypothesis, takes the next slice, and again applies it to the right, displaces it to the right, I'm sorry. But this time the displacement is a little bit lower than the first, how far the first slice was displaced. And again, hypothesis 2, this guy has a larger probability of generating a click than the first hypothesis. So if a click does occur, which is what I'm showing by this cross, the receiver internally changes its mind. It has now switched its belief to hypothesis 2 being true, because a click did happen, and hypothesis 2 was the more likely to have generated the click. So when it goes to the third slice, time slice, it now displaces it towards the left of the origin, because Dolinar now wants to have a detector's click prove himself wrong. And again, this time I'm showing this example, the hypothesis 1, which is more likely to generate a click, does generate a click, which is what I'm showing with this cross. Remember, this is time. Then again, it internally switches its mind and just starts displacing the next slice onwards to the right and keeps going. And the hope is that by the time you are halfway or almost done through the pulse, that you will have the correct hypothesis in mind, and the displacement approaches what Kennedy would have done in his exact nulling case, where you displace it such that the correct hypothesis, the one that is really true, is the one that is displaced close to vacuum, so that the subsequent detection events do not generate a click, so you never change your mind, and at the end of time you generate a guess that is the right hypothesis.
A question here is, does Dolinar receiver need asymptotically long pulses in order to
No, not at all. Not at all. That's a very good question. T can be anything. Remember that the error probability formula, if you have an asymptotically long pulse, the error probability will become 0, right? This error probability will end if you have a constant rate, constant watt laser pulse. If you make T large, your mean photon number is also going to become large, and this probability of error is going to approach 0. But Dolinar receiver works for no matter what n is. And that's the beauty of this receiver. It's a beautiful receiver design. I would encourage you to read his thesis. But as I said, this doesn't work for 3 or more coherent states. Kennedy receiver, now you can think of that as a very, very special case of a dumb Dolinar receiver, where you just displace all the slices by the same amount and you wait for the first click. You don't even need to have the subsequent clicks, and you make a guess. Okay, so I had already shown you this plot. I just wanted to show it to you again. This is the black line, the Dolinar receiver. So it's a factor of 2 or 3 dB better than homodyne detection in the error probability exponent, meaning how quickly the error probability dies with increasing mean photon number. obvious question, how does this work with multi-letter modulation formats like query phase shift keying? So you can do the same thing. You slice it up into k slices and you make an internal belief in your receiver that switches not between hypothesis 1 and hypothesis 2, but maybe goes through a circle. 1, 2, 3, 4, 1, 2, 3, 4. So you first take the first slice and null hypothesis 1, you displace it to the left so that the first hypothesis is sitting in vacuum. And if you get a click, you change your mind to hypothesis 2. And if you don't get a click, you keep nulling the hypothesis 1 and just keep doing that until you get a click that makes you rule out hypothesis 1. You go to hypothesis 2 and keep nulling that and so on. This receiver was studied by Roy Bondurant in 1993. And he found the probability of error achieved by that. But unfortunately, this time, he was not able to get to the Hellstrom limit, the minimum probability of error. Okay, so the optimized nulling Bondurant receiver, it is the equivalent of the Dollond receiver. It doesn't get you to the Hellstrom bound. The Hellstrom bound is that minimum probability of error. So the simplest non-trivial example beyond binary is obviously ternary. If you have, say, this is for people who do classical communications, they would call this modulation format a binary phase shift keying with return to 0. It's just a name, BPSKRZ communication. So you have 3 possibilities, 0, alpha, and minus alpha. And let's say you have equal priors on all these 3. What is the minimum probability of error? So you can solve those YKL conditions. First, I have to write down the pairwise inner product between these 3 coherent states. This is called the Cram matrix. And then, if you remember, we just have to calculate these Xij's, which is the inner product between the measurement vectors and the state vectors. So I'm basically aligning 3 orthogonal vectors, W1, W2, W3, with respect to these 3 non-orthogonal vectors, which are my states. And I'm not going to go through the math, but you can write down those YKL simultaneous equations and then solve them. And if you solve them, you cannot solve this analytically. You have to solve it numerically, partially numerically. But if you plot this probability of error, you will get this formula. This is actually from a picture from Carl Hellstrom's book, which is still my go-to reference for everything to do with quantum detection estimation theory. So somebody asked a question about a book. So I would recommend this book highly for detection estimation theory. For information theory, there is a book by my colleague Mark Wilde. It's called Quantum Information Theory. It's a beautiful book. It doesn't go into optics, but Alexander Holevo has written a book on quantum information theory that does go into optics. And has less information theory, more optics. Anyway, for 0, alpha, and minus alpha, if you were to do detection right now in the lab with current equipment, what would you do? You would use homodyne detection. You would get 3 Gaussian random variables with mean minus alpha 0 or plus alpha with a variance of 1/4. Right? You can write down the error probability of homodyne detection. You can show that is given by this ERFC formula. You plot that, get this formula here, this plot here. But the YKL condition, the minimum probability of error, will give you this. And you can show that this minimum probability of error goes as e to the minus n, whereas the probability of error for homodyne goes as e to the minus n over 2. So there's still that 3 dB improvement in the error probability, which amplifies as n becomes larger. So Dan Kilper, to your point, it's interesting that, even though these quantum effects become important when n is small, the performance difference between conventional receiver, the way we think about homodyne, heterodyne receiver, and these receivers that use optical pre-processing, it actually amplifies when n increases. And what this translates into is an improvement in the error probability exponent, which translates into the latency of communications. If you have a short burst communication that you want to send with a low probability of error, these kinds of receivers can give you a better performance. So there are different use cases of quantum receivers or non-standard receivers. Well, so a Kennedy-like receiver can get you that exponent, but doesn't exactly achieve this minimum probability of error. So this is your last problem for the first module. Very simple problem. Pulse position modulation. So pulse position modulation is I have m possibilities. I now have m time bits. And I'm going to excite only one of the modes, one of the time bits with a coherent state alpha. So there are m possibilities. Alpha could be either in the first time bin, second time bin, third time bit, but all the other time bins are 0, and you got to figure out where that pulse is. So the receiver that you're going to use is direct detection. And by the way, this exact modulation format, pulse position modulation, was the modulation format of choice for the MIT Lincoln Labs Lunar Laser Comm demonstration program. This is a very popular modulation format for low photon number regime. So your job is to find out what is the average probability of error you will make if you use photon detection and assume ideal photon detection. This one, I'm going to give you 1 minute to work out, and then we'll proceed. Okay, so let's go ahead and show the poll answers, Brianna. Okay, so there's a tie between, okay, great. So we kept a record every time the highest fraction of the answers is the correct answer. So the correct answer indeed is C. Interesting that a third of the people found e to the minus 2n over n. And the reason it is the answer C is correct is because the photon detection, the way you can make an error is that you don't get a click where the light is, and that happens with probability minus n. But even when you don't get a click, you could still make a random guess, and that random guess is going to fail with that probability of error. So answer A was almost right, but answer C is truly the correct answer. Okay, thank you. So for PPM also, because this is the error probability of direct detection that you just derived, I can ask the same question about sort of what is the minimum probability of error? Well, this time I can solve those YKL conditions, and this time I can derive a nice formula and write it that for formula. And Dolinar derived this in his PhD thesis, but we don't know how to design a receiver that gets to that. But there is a receiver that uses conditional nulling, meaning it applies a nulling to the first time slot. If it was a coherent state alpha, it brings it to 0 and then detects it. And now, if you get a click, you rule out that first hypothesis and you go null the second time slot and keep going. And if you don't get a click, you retain that hypothesis. This box is showing what is your current hypothesis in your mind, and you simply direct detect the rest of the time slots without nulling. And if you get a click on time slot K, it must be the kth code word that was received. So this receiver called conditional pulse nulling was invented by Dolinar, and then we improved it using what is called squeezing. Christos will talk about that, which can attain a probability of error that has that gets almost to this YKL limit. This is this black line, but not quite. And the gap is the largest in the low photon number regime. If you can amplify that, that's what the gap is. In the high photon number regime, this almost closes the gap. But again, this is factor of 2 improvement over direct detection. And in my former group at BBN Technologies, we did an experimental demonstration of this receiver about 10 years ago and showed an actual improvement in the error probability, about 2.3 dB error probability improvement for 4 ppm is what we did in this major photonics paper. So those are the experimental plots, and these pink dots are performance points that are below what you can get with idealized short noise limited direct detection on 4 ppm. Okay, so that brings me to really the conclusion of the first module. So we in this module dealt with only 2 physics concepts, interference and photon detection. We were just playing with these 2 things. Now, and I showed you how we can calculate the minimum probability of error for discriminating any set of coherent states, yet we don't know how to design a structured receiver design for n greater than 2. So n equals 2 case was special, that there was a receiver design. But then so far we have only been playing with these beam splitters or linear optics, passive linear optics, and direct detection. These are not universal resources. These are not, you cannot do everything possible by the laws of physics by just these 2 things. But then, as Christos will tell you about, the moment you add this thing called squeezing to our toolbox, for which you're going to need more advanced quantum optics math, then our toolbox will become universal. Now, Christos will teach you what squeezing is, but to give you an insight for what that might mean in terms of these receiver designs we are talking about, if you take this coherent state alpha and you apply squeezing to it, which is a unitary transformation that can be implemented by a chi2 nonlinear crystal that I mentioned at the very beginning of the lecture today, pass the light through this optical parametric amplifier in the quantum limited regime, which you can build in the lab. What you can do is that you can bring the light, the state of the light, to this funny state. I'm showing this elliptical shape here. And this ellipse represents the fact that if I were to do homodyne detection along this quadrature, I'm going to get a smaller noise variance compared to homodyne detection along this quadrature. And this circular cloud around alpha coherent state shows that no matter which quadrature I measure, I always get that 1/4 variance of that homodyne detector's output. But now for squeeze state, that 1/4 changes to 1/4 times e to the minus 2r if you measure along this quadrature, and 1/4 times e to the plus 2r if you measure along this quadrature. But the mean also shifts from alpha to alpha times e to the minus r. Well, so homodyne detection, if you do after squeezing, it doesn't quite change the error probability for BPSK modulation. But if you do direct detection on squeezing, after squeezing the pulse, you no longer get Poisson point process. So if I take a mode of light and I excite that in a squeeze state and then put it into an ideal detector, I will still get random click events. But to describe the statistical properties of that random process, you're going to need a birth-death process, whose details were derived by Jeff Shapiro and Horace Ewan in a series of 3 papers in 1979 through 1981. But if you just ask the question, what is the probability that I will not get a click? Instead of that being e to the minus n, it gets a more complicated formula. And this formula reduces to e to the minus n when r equal to 0. And this result is a quantum result. I cannot even describe this to you using Poisson short noise or semi-classical theory of photo detection. But I can use that as a toolbox. So for BPSK, for example, this paper in 2008, they did a very simple trick. They said, well, take Kennedy receiver, where you apply a displacement before detection, but after displacement, you apply an optimized squeezing and then detect. And they show that you can get a tiny little bit improvement over what you could do with Kennedy receiver. Although it doesn't get to the Hellstrom bound, but this is a tool. So in a general design of an optimal receiver, I just told you that squeezing, linear optics, and photon detection is universal. That has been proven. So there must be some way to put these things together to write down optimal receiver designs for this Emery state discrimination problem, but it's an open problem. We don't know how to do that. So, but then there's another philosophy, is that instead of just designing this all optical receiver, this in an optical domain, what if I took each of the coherent states and loaded the state of the coherent state into a single qubit? Remember, I told you that alpha and minus alpha, 2 vectors that can be embedded onto this onto a 2-dimensional space, and because there's just one scalar inner product that matters. So there should be a way, because alpha and minus alpha has the same inner product as these 2 states, there should be a way for them to map a coherent state of alpha or minus alpha into the state of a single qubit state, either psi1 or psi2. Now, that's a hard thing to do, but if you could do that, the rest of the receiver design problem just becomes a tiny quantum computer, which brings back to this example that I started out with. So that optical receiver could be a mini quantum computer after that transduction step. And we tried this. In this paper that we just published with Prineha Naran's group, we took that small quantum circuit for this a 3-bit code and a 5-bit BPSK code, and ran it on Honeywell's trapped ion quantum computer. We wrote a Qiskit code for this quantum circuit that we developed in a previous paper and ran it, and we got a tiny little bit of improvement over the best possible symbol by symbol receiver that exists. To end with, I want to come back to a question that Dan Kilper asked in the chat window. I won't have time to go into communications capacity, but I just wanted to give you the flavor for what is the meaning of capacity. So far, we have been just playing with probability of error, of telling apart between states of a single mode. But you can ask this question that, let's say this is the kind of code word you are getting in a BPSK modulated signaling. Each of these pulses have a mean photon number of n, and you can excite them in any state you want. Your alpha can be either phase or amplitude modulation. Alpha can be a complex number. And you can ask the question, how many bits of information can I encode per pulse faithfully? And you can ask this question, and the answer for, let's say, BPSK modulation is given by what is called the Holevo capacity. It's another quantum metric like the Hellstrom limit, but that tells you the best possible capacity you can achieve. So C of n is the bits per pulse. And if I'm divide that by the mean photon number per pulse, I get bits per photon. I'm putting that on my y-axis and the mean photon number n on the x-axis. And now you see that the Dolinar receiver, which detects every pulse one at a time, minimizing the probability of error for detecting every BPSK pulse, its capacity or bits per photon is given by this blue line, whereas the hole level capacity is far above that, even n is very small. So when n is very small, there is a receiver design that I proposed a little over 10 years ago called the green machine, which right now my colleague Lynn Ran Fan at the University of Arizona, in collaboration with a few people at NASA, are actually building in the lab. You could get a capacity improvement over what the dollar receiver can achieve by using joint detection. Joint detection meaning a receiver must act collectively on many optical symbols at a time. But then this performance that can be achieved by this green machine to bridge the rest of the gap all the way to the hole level limit will require joint detection receivers, but that also use quantum effects like squeezing internally within the confines of the receiver. And if you don't restrict yourself to BPSK modulation, you can find the best possible hole level capacity with no restrictions on the modulation or the receiver. So what you can do is ask the question of what is the hole level capacity for a given modulation format? And you can also ask the question, what is the ultimate hole level capacity with no restriction on the modulation or the receiver? And Shannon capacity, which many of you are probably familiar with, becomes a special case of hole level capacity, which asks, given a modulation and a receiver, which induces a noise process, what is the best possible capacity you can achieve? So this is the subject of information theory, and hole level capacity is the subject of quantum information theory. In this plot, on the x-axis, I have spectral efficiency, or bits per second per hertz, or bits per pulse, C of n. Y-axis, I have photon efficiency, bits per photon. So I cannot, if I try to push more data in the high-end regime, I would, I'm interested in spectral efficiency. This is the regime, say, for traditional fiber comms. Photon efficiency, I'd be interested in if I were NASA or JPL doing deep space communications, a low-end regime. All of the non-black lines are the Shannon capacities for given modulation formats and receiver designs. So notice that in a low-end regime, direct detection is the best thing to do, which is why that lunar laser comm demonstration program used PPM and direct detection. They were driven by a Shannon capacity, this blue line. So they were trying to, Don Boroson's program was operating right around here. Whereas for traditional fiber comms, QAM modulation, heterodyne detection, you're operating over here. Okay, so it is this regime where there is the most improvement to be had with joint detection receivers. In the high-end regime, capacity-wise, heterodyne detection receiver is already pretty good. But as I said earlier, you can get a higher, this lower error probability per symbol translates to a lower latency of communications. And I won't have time to go into that. So concluding remarks, we talked about laser light pulses undergoing wave-like interference, much like ripples of water in the pond. When you throw two stones, 2 points, and the ripples interfere on the water. Laser light field cannot be precisely measured. There is an inevitable noise that will corrupt your signal no matter how you detect it. But knowing what you are trying to detect, knowing what you're trying to do to that information-bearing light, you can be more clever about designing the receiver rather than just blindly detecting the light and then post-processing using whatever in the electronic domain. Detecting photons on a laser light pulse or a coherent state produces a random number of clicks with a Poisson distribution. Quantum representation of a laser light pulse is a coherent state, and this representation helps us quantify the best receivers, for example, that minimize the probability of error or maximize capacity or minimizes the estimation fidelity, even without knowing how to build such an optimal receiver. Just using semi-classical tools, meaning this interference and Poisson short loss limited photo detection that we covered, the two physics topics I covered, one cannot attain in general the quantum limit of any sort of optimal receiver performance in most cases, except for special cases like the Dollar receiver to coherent states. And the optimal receiver designs require some form of a quantum processing of the laser light. You can do it either all optically, using squeezing, linear optic photon detection, feed forward, and so on, or you can first couple the states of laser light pulses into qubits, like trapped ion, color centers, neutral atoms, cold atoms, whatever is your favorite qubit format, followed by processing those qubits in the native quantum computer. Okay, so hope you enjoyed this module. And with that, should we take maybe a 2-minute break and then can go get started?
Okay.
So you can, Christos, if you want, you could come over here if you want to. Sure, I'm going to go ahead and mute myself. let me answer this question live. Mike Kramer has a question. Why does the green machine require internal squeezers? No, it is not muted. So the green machine actually does not require squeezers. Let me go back to the green machine for a second. So the green machine, here. The green machine only uses passive linear optics and photon detection. So it is not using any non-classical effects within the receiver, but it's a joint detection receiver. It is converting BPSK modulated Hadamard code words into pulse position modulation with coherent states prior to detection. But that helps us improve capacity far beyond what you can get by even the Dolinar receiver that detects every single BPSK symbol at a time. We had this student, Haiwan Chung. She is now a faculty in KAIST in South Korea. Back in 2010, I led a DARPA program project called Information in a Photon. It was out of DSO that Mark Neifeld ran. Haiwan's entire PhD thesis, Mike, was can we develop what is the performance of the most general Dolinar-like receiver that does not use squeezing within the confines of the receiver, but does use interference across the whole code word and use feed forward, local oscillator, but everything is semi-classical. And her PhD thesis ended up in this negative result. And this was, she was Li Zhongzheng's student at MIT. And the negative result said basically that no matter how hard you try, if you don't use anything that cannot be semi-classically described, like anything beyond linear optics and photo detection, coherent states, you cannot bridge the rest of the gap to this capacity. I'm now not mathematically defining what rest of the gap means, but it is a scaling difference in how the C of n scales in the low photon number regime. So I hope that answers the question, but that's a very interesting question, Mike, that we are currently interested in. Linran's group and my group, we are currently funded on a NASA contract where we're actually thinking exactly to your question that can we include squeezing in some clever way within the green machine or something similar that can get us further or closer to the level capacity. And that would be of interest for deep space communication. And the motivation behind this project is that the deeper you go in space, the lower n becomes. Like instead of lunar lasercom, NASA has now launched their Mars lasercom program. And the lower the n is, the gap between joint detection and direct detection amplifies. So that leads us to ask, like, are there better receivers that can get you, further out or work with a lower laser power to get a certain data rate? So I hope that answers the question, and I'm going to turn it over to Christos.
Let's start now. Or
Yeah, I would say let's go ahead and get started.
Or maybe we should allow a break. People are tired.
Okay, so just we get started. There's a question: Are there slides for the next statement available? Yeah, they are. They are like the same package, the same PowerPoint file that Saikat has been using. Okay. Okay, that's great. So I will be talking about some very basic stuff of quantum mechanics. Then we will play a little bit with some calculations on beam splitters. Then I will introduce Gaussian multi-port interferometers, and I will try to convince you that all of these things can be applied to, not only to number 4, but to several other things. But I will emphasize that quantum mechanics and purely quantum light can be used in what we call Gaussian boson sampling, which is a specific type of quantum computer that calculates samples for what we call a Hafnian or a permanent. Maybe. Sorry for that, please.
You have to first click once in where you want.
Okay. Now, quantum optics, quantum mechanics essentially is applied linear algebra. And as far as I am concerned, this is the end of story. What is a state? A state in quantum mechanics is a vector which is defined on a Hilbert space and describes fully the physical system. That is a pure state. How and why? Well, if you have a Hilbert space, then you can have some Hermitian operator H, and you can use the eigenvectors of that Hermitian operator as your eigenbasis to represent any state psi on the specific eigenbasis, which are multiplied with some complex numbers which are called CK. Okay. Now, what do I mean when I say describes fully the physical system? I mean that I can get information on the state, that means on the physical system, by expressing my state, that means my vector, on some specific eigenbasis. What kind of information I get? Well, usually the relevant things to think of in quantum mechanics are two things, are mean values and probabilities. For example, I have a specific Hermitian operator, which is the number operator. And all of us, I assume we know what a quantum harmonic oscillator looks like and how to solve it. So I will use that specific number operator, okay, which describes the quantum harmonic oscillator. I will use these eigenvectors, and I can express my state psi on that specific eigenbasis. Now, I can pose the following question. What is the probability of detecting M photons on the specific state psi? Well, that is simply the overlap of my state psi overlapped with some Fock state that Saikat introduced M modulo square. And from there, it's just a straightforward calculation, calculate the probability of finding M photons in my state psi. Now, you can repeat the same thing with any other kind of Hermitian operator. For example, this Hermitian operator H is not N operator anymore, it can be like the position operator. So you can ask, what is the probability of my physical system, which is described by the vector psi, to have some specific canonical position or some canonical momentum, and so on and so forth. Now, I don't know why it's moving by itself. What about mean values? Well, it's the standard definition of a mean value in quantum mechanics. You sandwich the operator you're going to find the mean value of in between the states psi. And if you, for example, expand this state psi on the Fock basis, and you do very few steps, you will be convinced that it is M, the number of photons, multiplied by the corresponding probability of having these M photons in your system. And you can repeat the same process for other kinds of Hermitian operators and calculate what is the mean value of the canonical position, the mean value of the canonical momentum. You can calculate variances. For example, what is the variance of the photon number, what is the variance of the canonical position, the canonical momentum, and so on and so forth. Now, what is a mixed state? A mixed state is simply defined as a statistical mixture of pure states. So this psi with index k I have over there, they don't have to be orthogonal to each other. It's just some random states I chose out of a bag. I multiply each one of these states with some probability qk, and I sum them up. That defines a mixed state. Now, the constraints here is that qk are some real positive numbers, which they should sum up to 1 because they have the interpretation of probabilities. What probability? The probability of finding the state psi k within the bag that I define as a mixed state. Okay. Now, this index k can be continuous. It doesn't have to be discrete. For example, in that case, you don't sum over k, you integrate over the continuous version of k, which is x. Okay. Now, q of x is a proper probability distribution function. And by proper, I mean is non-negative. And if you integrate q of x over all x, that equals to 1. That means it's normalized. Now, the mean value of observables, for example, the mean value of the photon number operator, n hat, is found if you find the mean value for the photon number operator for every psi k, and then you average again all possible probabilities that psi k's have to happen in your mixed state. So that means you can write like in a very common way that n bar, the mean photon number, is if you trace together the n operator with your mixed state row. Okay. Now, what is a continuous variable system? Well, continuous variable system simply means that we use states of light to do our quantum information tasks. as far as I said, I mean, the most essential CV state, because you start to build everything from that specific state, is the coherent state that Saikat introduced in the previous module. I chose to define it like that. I mean, as I said before, you can take any state and you can express in any basis you like. Here, I express my coherent state alpha on the Fock basis. It looks exactly like that. Well, I like to say it in the other way around. I like to say that I choose to define it like that because I know that I want to describe Poisson statistics upon photon counting, upon photon number measurement. So I define it like that because if I go and calculate what is the probability of a state defined exactly like that to find m photons in that state, I will get the Poisson distribution. Okay. Now, a classical field can be excited into two kinds of states, or one kind of state, if you like. We will see what I mean by that. It can be a coherent state, which is simply ideal laser, or it can be a statistical mixture of different coherent states. Now, somebody in the previous module asked what is a classical state and what is a non-classical state. Well, the answer is simply that a classical state is any state that you can write in this form, where this P of alpha is a proper PDF, a proper probability distribution function. If you cannot do that, or if you can do that, but you find that your P of alpha is not a proper PDF, for example, is negative, or for example, is even imaginary, or is like something like derivative on some weird function like the Dirac delta function, then your state is non-classical. Okay. Now, we have the states. Then the question is what we do with them. And by that, I mean how to transform the states. Here I have a few examples. I mean, you can apply any unitary on any state and obtain another state. Okay. But several unitaries are more important in quantum information processing than others. And these are what we will examine in this module. For example, you can do a phase shifting. I define a unitary in such a way that if I apply it on a coherent state alpha and I do all of the math properly, then I will end up with a different coherent state where on some phase space, some diagram where this is the canonical position of the field, and this is the canonical momentum of the field, and this is the alpha I start with, I just rotate my coherent state by phi, and I get another complex number on that phase space diagram. Now, I can calculate mean values, and I know how to do that, because I can express my states, for example, on any basis I like, for example, the Fock basis. I showed you the formula to calculate mean values, and variance is nothing but a difference of two different mean values. It's like the mean value of Q square minus the mean value of Q square outside that mean value. And I can find the variance of the canonical position, the canonical momentum, and I find that for the coherent state, in the specific choice of units, h bar equals to 1 in everything I'm doing, equals to 1 over 2. Now, you can apply what we call the squeezing operator, the single mode squeezing operator. For example, you can start with a vacuum. I define a unitary like that. I choose to write everything on the Fock basis. I do the math. I know how to apply a unitary on a state. There are easier ways, there are harder ways. No matter what you do, you will end up to the same final state. And this is how we derive what we call the single mode squeezed vacuum state. And again, if I plot everything on some phase space diagram, this is vacuum, where I start from. This is like a coherent state where alpha is equal to 0, if you like. Or you can view it as a Fock state where n equals to 0. It's the same thing. If I apply my squeezer on that state, I will get a different kind of shape. And that justifies why I call it a squeeze state, because here I squeeze one of the two quadratures depending on how I define my unitary operator. I mean, I can define my unitary operator in a slightly different manner. Of course, this form A squared minus A dagger squared will remain more or less in place. And in that way, you can squeeze in different kinds of quadratures. So here I chose to squeeze the P quadrature, and that came in the expense of having a larger variance in the other quadrature. Okay. Some other details I don't mention here is that the area of this disk and this ellipse are the same. And that implies essentially that unitary operators should respect commutation relations. The third operator I want to introduce here is the so-called displacement operator. For example, you can start with some vacuum state like before, and not squeeze it, but displace it. That means you apply this kind of operator, you choose a proper basis to do the math the easiest way possible, and you go from the coherent state with alpha equal to 0, you go to a coherent state with amplitude equal to some complex number beta. Now, a nice way to describe quantum optics, especially if you work with CV quantum information systems, is to introduce the phase space description. I mean, I will not go very deep here in the phase space as I do in my course here at the U of A. But the cool thing by doing that is that you avoid using the Hilbert space. There is a way, I want to say, that you can take any state, raw, mixed state, and map the operator to a function. Okay, this is done by the so-called characteristic functions. Okay, I'm not going to the mathematical details right now, but it is a known fact that no matter if you calculate whatever you want to calculate by using the density operator rho, or if you are using any of these characteristic functions, the characteristic functions represent full knowledge of the state, just like working with rho. Okay, and the good thing is now you have a function in your hands, you don't have an operator. And for once, you can make nice figures, as I will show you in a little bit. Now, you have three characteristic functions. You can do a Fourier transform in all of these three characteristic functions, and this is how you derive the so-called quasi probability distribution functions. For example, if you take this one and you do a double Fourier, you get the Q function, the Husimi Q function. If you take this one and you do a Fourier, you get the Wigner function. And if you take the last one, the normally, as they call it, normally ordered characteristic function, you get the so-called P function. Now, each one of these, they have their own value, depending on what you want to do. For example, the Q function, no matter what state you are examining, is always positive and normalized, of course, to 1. So this is always a proper PDF. Now, the Wigner is probably our favorite one, I guess, and that is because it can take negative values. So it is not always a proper PDF. However, as a mathematical tool, it's very useful because no matter what mean value or probability you are trying to calculate, using even the partly negative Wigner function, the answer will be correct. But we have to state that it is not always a proper PDF. And especially the states that exhibit some Wigner negativity are the most valuable in several quantum information tasks, just like quantum computation. Now, the last one, the P function, is not always a proper PDF. It can be like derivatives of some Dirac delta function or negative or imaginary. And as I said before, if it is a proper PDF, then the state is classical, and that goes the other way around. If the state is classical, then the P function is always a proper PDF. Okay. A little bit more about unitary evolution. In quantum mechanics, we have the Schrödinger picture, which means that I apply the unitary that describes some transformation on the state, aiming to derive the new state. Or I can imagine that the states remain like stationary, but I change the operators. This is the so-called Heisenberg picture. This is very useful because in quantum optics, we really like, and it's more convenient to work with the Heisenberg picture by transforming the field operators A and A tagger. Okay. Now, what I do here in these steps is I try to demonstrate how to transform the characteristic functions using Heisenberg picture. So what I do here, okay, I start with some state rho. Through that, I define the three characteristic functions, and then I ask, okay, now I do something to rho. I apply the Schrödinger picture on my state rho, okay, which is this thing. Now, the characteristic function is defined through this trace, and in trace I have cyclic property, okay, I can permute in a cyclic way operators that I see within the trace. That means that I can take this U and put it here, and then from functional analysis, I can just put the U dagger and the U, which are from the left and the right of that exponential operator, inside the exponential itself. So instead of changing rho, I can change in the Heisenberg picture now, A and A dagger. Okay. A definition I want to make here is that a Gaussian state is a state whose characteristic functions are Gaussian in the Gaussian form. Okay, for example, if you prove it for any of the three characteristic functions or for any of the three of the quasi probabilities, you're done. If one of them is Gaussian, all of them will be Gaussian. Okay. Okay. So if you want, for example, to see if a state is Gaussian or not, you go and you calculate the Wigner function, and if you find that a form exactly like that, then you have at your hands a generic Gaussian state. Okay. Since it's in the Gaussian form, any Gaussian state is defined through two pieces of information. That is the covariance matrix and the displacement, and that is all. And if you know how to transform these guys, then you know how to transform the state in general. Now, a Gaussian unitary operator is any unitary operator that takes you from a Gaussian state to some other Gaussian state. It preserves Gaussianity, if you like. Okay. Now, in 2 slides before, all of the operators I discussed were what? Were phase, single mode squeezing, and it was also displacement. These are single mode operators. If you want to create entanglement, you need a 2-mode operator, okay, to complete the set. Also, the operators I showed you before, the squeezing, the phase, and the displacement, are Gaussian operators because they map Gaussian states to Gaussian states. The beam splitter is another Gaussian operator, but it's not single mode. It acts simultaneously on 2 modes of your input field. And that creates entanglement. So now you have an expanded set of Gaussian operators, which means that you can create Gaussian entanglement if your input state is Gaussian. Now, as Saikat gave you the expression before, in the Heisenberg picture, the output, annihilation, and creation operators, okay, A out, B out, live here, and A in and B in live here, is described through this transformation. Okay, so the leftmost side of this equation is the output, and the rightmost is how it relates to the input field operators. Now, it's a simple exercise, but we'll not do this type of exercise right now. If you inject a single mode squeeze state here and a single mode squeeze state here, but with a small difference, this is R, this is minus R. That means that they are squeezed in opposite quadrantures. And you pass them through a balanced beam splitter. Now that means transmissivity is 1/2 is a 50-50 beam splitter. Then we create what we call a 2-mode squeezed vacuum state, vacuum semicolon R, as I denoted, which is a state which among all 2-mode pure Gaussian states possesses the highest amount of entanglement. This state, as Saikat defined before, an entangled state, we can see quite easily that this entangled state from its form, if we write on the Fock basis, because it's impossible to break it as a tensor product of 2 other states. Okay. In general, a pure state that cannot be written as a product of 2 states, we call it an entangled state. Now, some examples of states of light. There are 4 possibilities. We have classicality and we have Gaussianity. Okay. Now, coherent state, for example, is classical and Gaussian. Why classical? It is classical because the P function, if you go and calculate it, is a proper PDF if you like to view Dirac delta as a proper PDF. I will come back to that in a minute. Another example of classical and Gaussian is a statistical mixture of coherent states under some Gaussian distribution, something like what we call a thermal state. Now, a state can be classical, but non-Gaussian. For example, you can have the statistical mixture of two different coherent states. Both of these states are classical, and I mix them together under some classical, if you like, PDF. Okay, 1/2, I have alpha, 1/2 probability, I have beta. This is a classical state. However, if you go to calculate the Wigner function of that, or any other of the characteristic functions, and then do the Fourier, you will find that this is a non-Gaussian characteristic function. Therefore, the state is non-Gaussian. A state can be quantum, but Gaussian. A prime example is the squeeze state of light. If you calculate the Wigner function, you will find it's like has a very nice Gaussian form. But it is quantum. First of all, you need field theory to derive the existence of the state. But the simple way to see that it's a non-classical state, a quantum state, that means, is if you go to calculate the P function. Okay. If you go to calculate the P function, it depends on what exactly squeeze state you are dealing with. In general, you will find that is a function that looks like a PDF, but it's multiplied something like -I, where I is imaginary unit. So the P function is not a proper PDF for the single mode squeeze state or for any other kind of squeeze state. A state can be quantum and non-Gaussian. A prime example is the Fock state, because if you go to calculate the P function, you will find that is the nth derivative of some Dirac delta, which is not a proper PDF. That makes it quantum, and is non-Gaussian simply because if you go to calculate the Wigner function of a Fock state, you will find that can be negative. Okay, which means it's non-Gaussian. Now, the Gaussian set of transformation consists of a phase, which is a one mode to one mode operator, the beam splitter, which is two mode to two mode operator, the single mode squeezing, which is one mode to one mode operator, the displacement, again, on one mode to one mode operator. This defines the Gaussian set, but it's a well-known result that you cannot attain universality if you stay within the Gaussian regime. You need to expand the set with at least one non-Gaussian operator. For example, you can do the cubic phase here, sorry, and complement the set with something non-Gaussian. So now you have something which is truly universal. Of course, implementing non-Gaussian operators is something extremely difficult, and how to approximate useful states to quantum information is a very interesting topic that our group works on, and many other good groups work on as well. Right, this is what I want to say. Now, let's do some calculations. Okay, this is like a winter school, right? I mean, we're supposed to do a little bit of math sometimes. Let's do the following. Let's take coherent state and vacuum, okay, as the input of some beam splitter, okay? And let's take as a given the Hansberg relation between the output field operators and the input field operators, okay? How to calculate that? I mean, how we do math in quantum optics. This is a very standard example, I guess. Well, for now, I choose to work like on the Fock basis. So I take my state, I know how to write my coherent state on the Fock basis. So the joint state in the input would look like that. Then I do a small trick here. I take this n back and I write as creation operator n times acting vacuum, divide by some proper constant, because this is how we define the ladder operators. Okay. Okay. Then I start with the Hansberg picture. I say, okay, I need to find psi. This is my input state, and this unitary here is the Schrödinger unitary that describes the beam splitter. Okay. I act with this on the state written in this form. Okay. Now I do another small trick here. Exactly here. Okay, so this UBS is this UBS, and here I have nothing. Nothing means I have identity. Identity is U dagger multiplying U, because that thing is unity. Okay, so I have UBS acting on vacuum. UBS acting on vacuum will just give me vacuum, because if I mix two nothings together, I will get nothing, if you like. Okay. If you inject nothing into a beam splitter, the beam splitter will give you nothing, and nothing in quantum mechanics means vacuum state. Okay. Here I have something more interesting. I have the sandwich of U, A dagger to the N, U dagger. You can convince yourself, since this U is unitary, that you can rewrite it as this. Okay. Now here I have something really nice. Here I can use the Heisenberg relation. Okay. Essentially, this thing is this first line here. And I do exactly this. I write like that. Then I use the binomial expansion theorem. So I break this bracket to the N as the summation over L here. Okay. I'm sure that all of you can follow these simple steps from this line to this line. I write a few terms. I rearrange a little bit my summation. And what I get at the very end is exactly this relation, which means that I can view like as a product state. I mean, this is state up to here, number one, and this second state is another state. And I can recognize what these states are. They are nothing but two coherent states. So when I have alpha and a vacuum in a beam splitter, what I get is a product state at the output of a coherent state with damped amplitude alpha. Alpha, that means multiplied by square root of the transmissivity. And on the lower port, I have alpha multiplied by 1 minus the transmissivity. Okay. Of course, and I have to stress this out, that the total energy is conserved if you transform your state through a beam splitter. So that means that the mean photon number here is modulo alpha square. The mean photon number here should be again equal to modulo alpha square, and exactly this is what you get, because you separated the amplitude in that specific way. Another interesting thing that happens here is that I used a beam splitter, and I used a classical state. I used a coherent state. Okay, and that's why I don't see interesting things going on. Okay, for example, I didn't create entanglement here. You cannot create entanglement with coherent states in beam splitters. You have to do quantum stuff to get entanglement. And this is exactly what I'm doing here. Okay, so now we start building how interference works in quantum mechanics, because now I will use the same transformation. I will use the beam splitter, and on top of that, a simplified beam splitter, because I don't have any phases. I assume that my beam splitter is like balanced one, tau is equal to 1/2. But my input state will be a quantum state, quantum and non-Gaussian as well. It will be a Fock state here and vacuum on the other port. So the quantum stuff happened here on the Fock state. And the question is, what is the input state? Again, I do the same kind of trick as before. Here is even more simple. Instead of writing 1 here, I write it as a dagger acting on vacuum. Okay. Then I inject identity exactly here. I know that nothing will happen when I hit my beam splitter on vacuum state. I will just take vacuum back. And this part here can be simply be applied like from the Heisenberg relation. I can just rewrite like that. Okay, so this is now a dagger out. And I know how to act with annihilation and creation operators on my vacuum state, and this is exactly the state I get. Now you see here that if I have a quantum state, I didn't got a separable state, I got an entangled state. Okay. Now you can do the same type of calculation. I will not go, I mean, I have the math here, but I will not like go through them. If you have Fock state here, number 1, Fock state here, number 1, so this is your input state. You pass it through the same type of transformation, balanced beam splitter. The question is, what is the output state? Okay, phi 1, 1. Again, the math is just a tiny bit more elaborated. You can work out what the transformation is. And what you get here is, again, of course, you have another entangled state at the output. And the remarkable thing on top of that is that the 1-1 contribution cancels out. That is because I used a balanced beam splitter. Okay. This is known as the Hungo-Mandel effect. and happens when your beam splitter is equal to 1/2. Okay. Now, you have essentially all of the math to start building interferometers yourselves. What I ask you to do here for that problem, I say here 7 minutes, it might take like less than that, is try to find what happens if I input in a non-balanced beam splitter a Fock state number 1 and a Fock state number 1 on the second mode. Now tau is equal to 1/3, not equal to 1/2. Okay. Okay, let's see the results. Excellent. Maybe people are more advanced than I thought they would be. Maybe they are better than I am. Okay, that's very good. Yeah, of course. It's A. First of all, you can do like a straight up calculation to find it. And the other way is to know or to observe or to believe me when I say that you have the Hungo-Mandel effect only if your beam splitter is balanced. Here is not. Okay, so B and C answers look more like Hungo-Mandel effect type of answers, while A is the only logical one. Okay, let's move to the next problem.
Let's move the poles to the right. Fixing there in the slide.
Okay. Notice. No, yes. Well, what I do here to give a little bit of explanation, I have a 3-mode system, okay, but 2-mode transformations, okay. First, you have the output of the first beam splitter, okay, which you know the answer to this, okay, these are both balanced. I have calculated the answer. And then whatever you get on the lower mode out of the first operation, you inject vacuum and you interact that output with vacuum on another balanced beam splitter, okay. 2 ways to solve it. One way is to do straight up calculations, of course. The other way is to remember that the beam splitter cannot create photons. It should preserve the mean photon number. Okay. So let's wait something like 3 minutes or so. Okay, in the interest of time, let's wrap up problem 2 and let's see the results.
That's great.
I don't see it. Oh, that's absolutely great. Okay. As I said, you can do the calculation, or you can remember that, I mean, I started off with 1 photon. So this 2-photon state doesn't make any sense where it came from, right? So this is the only logical solution. Let's do the break. Okay. Introducing multi-mode Gaussian interferometers. Okay, now I will define a few new things. That means that I need to change the notation a little bit. Okay, before I had, this is for the beam splitter again, okay, I had A out and B out. I mean, this is the upper mode of the output, this is the lower mode of the output. Now I will call all outputs, I will call them B. So B1 now is the upper mode of the output of the beam splitter, for example. And B2 is the lower mode, the output lower mode of the beam splitter, okay? And A will denote the input. So A1 is the input upper mode and A2 is the input lower mode, okay? I need to do that because I need to move to multi-mode stuff, and I need the indices 1, 2, then we'll have 3, 4, etc. to denote the number of mode I'm referring to. Okay, instead of changing the letter as I should have here. So now that is the beam splitter. It's a 2-mode operator, as we discussed already. Now again, this is the beam splitter again, but with renaming the operators A to be the input operators and B to be the output operators, where now I will count the mode I'm referring to. Okay, I hope this is clear. Again, nothing will change here. I mean, Schrödinger picture, Heisenberg picture, 1 mode, 2 mode, 3 modes, the mechanics of the math behind it are the same. Okay. What is the task? Because we are so obsessed with Heisenberg picture in quantum optics to transform the A and the A Dagger operators for each one of the modes. Now look what happens here. I have a field defined on many modes, n modes, if you like. Okay, and that's why I have A vector hat. What is A vector hat? A vector hat is a vector of all different annihilation operators I have in my system. A1 for the first mode, A2 for the second mode, AI for the ith mode, up to AN. Okay, so this is a bunch of annihilation operators, each one for each of the corresponding modes. In the Heisenberg picture, I apply my Schrödinger unitary on my operator. I do the same thing for the creation operators, and that's how I get a set of output operators, B and B Dagger vectors. Okay, so the end task and then task of the math and the initial point for most informational tasks is to know what this V looks like depending on the Schrödinger unitary you start with. I like to call this matrix, this is a matrix, it's not an operator anymore. This is a matrix that tells you how to mix together all of the different A's, all of the different A daggers, and then combination thereof, so that you get the output. Okay, so this is a matrix, and you see that I'm discussing Gaussian here. Why Gaussian? Because this is a linear transformation. Okay, which means that it will map any Gaussian form to some other Gaussian form. Of course, you need to respect commutation relations. That means that you start with a proper quantum system. That means that this must be equal to Kronecker delta Ij. That means that the output must be again a proper quantum system, which means it should respect the same commutation relations. So essentially, linear transformations with commutation relations is what we call in quantum optics symplectic transformations, which unites elements from the SU2 group and the SU-N11 group, if you know a little bit of group representation theory, which I will not discuss in this module. For example, in this kind of language, I can write the Heisenberg matrix of a beam splitter, let's call it V, exactly like that. I mean, if you now go and take V and multiply the vector A1, A2, A dagger 1, A dagger 2, you will retrieve the equations I had in the previous slides and Saikat had in his own slides. The phase shifter, another example, if you want to find the Heisenberg matrix V for the phase shifter, it is not difficult to find that V should look like that. So basically, when you apply a phase on a field, you have to multiply with exponential I times phi, the annihilation operator of that single mode, and e to the minus I phi times the dagger version of the previous equation I stated. Now, a small remark here that I want to do in order to avoid confusion, because I think I had that confusion like many, many years ago, is the following. Okay, what does unitarity mean? Unitarity in the Schrödinger picture and unitarity in the Heisenberg picture mean different things. In the Schrödinger picture, that means when I transform a state with some operator U, and that U must be unitary, it means that I preserve the normalization of the state. Okay, I preserve the norm of the state. I preserve a probability, if you like. The Heisenberg matrix V doesn't have to be unitary. Can you think why? Well, this is a very simple example here. I have like a proper transformation. This is a matrix V. This is how I transform my fields. Then I create this type of inner product. Okay, this vector with its own transpose conjugate. And I have this type of equation here. Now I say, what will happen if V dagger V equals to identity? That means what will happen if V is unitary? Then what I preserve if my Heisenberg matrix is unitary is the mean photon number. So V is unitary. If I started with a U, which is a passive transformation. Passive means that the transformation preserves the mean photon number. If you start with a unitary U, which preserves the mean photon number, then V will be unitary as well. If you start with a U, a unitary Schrödinger U, which changes the mean photon number, for example, squeezing, as we will see, then the corresponding V is not unitary anymore. Okay. A very small problem here. I give you what is the Hansberg matrix for a single mode, for a specific single mode squeezing operator. Okay. And I simply ask to verify if that is unitary or not. Okay, let's see the results. Well, most of you got it wrong. V is not unitary. I mean, with a small difference, I will call it. Correct answer is no. V is not unitary. Because this is hyperbolic cosinus and sinus. Okay. What you get here is that it preserves a different kind of matrix, not the identity matrix. It preserves the Minkowski metric, but we will not get into that. The bottom line is that V dagger multiplying V is equal to something I don't remember right now. I think 1 minus 1 in the diagonal, something like that, which is not identity, and that reflects exactly the fact that when you squeeze a state, you increase its energy, even though you keep the state to be normalized before and after squeezing, which means that the Schrödinger operator is unitary, but the Hansberg one is not. Okay. Now, the squeeze state does not have a proper Glober P function as a proper PDF, that means. Therefore, it is a quantum state. Believe it or not, I mean, all of the math have been laid out. I mean, it demands a little bit of effort and a little bit of experience to do this calculation. You can do it on phase space, for example, and then go back to the Fock space. But all of the math are more or less included in this module. If you take two oppositely squeezed states, one squeezed in Q, the other one squeezed in P, and you inject it like through a beam splitter, balanced beam splitter, you can calculate this state, and you can find that in the Fock space, it looks exactly like the state I showed you before, the two-mode squeezed vacuum state. Okay. If you move in something more general, I mean, for example, what will happen if I take a bunch of squeeze states with different squeezing value for each one, positive or negative, and I inject them through passive Gaussian unitary. Passive Gaussian unitary means that this is a unitary that preserves the energy. That means that the energy I have here, energy or mean photon number, I mean the same thing. That the mean photon number I have here and the mean photon number I have here will be the same. Also, these are Gaussian states. I assume that this is a Gaussian operator. So the state I will get here is the most general pure Gaussian state with zero displacements. I haven't applied a displacement operator anywhere for simplicity. If you assume that these states are not only squeezed, but also you apply a displacement operator in front of them, then indeed this G will become the most general pure Gaussian state. Okay, but for now I killed off all of the displacements. Okay. And what I mean here, I have a small abbreviation. What I mean by R1, I mean it's a vacuum squeeze state, okay, without any displacement. Okay, now the question is the following. I have this setup. I have here this G state, which is the most general pure Gaussian state with zero displacements. I ask, what is the probability of finding a specific photon pattern if I do a photon counting measurement. What is a photon counting measurement? I mean, we discussed that briefly before. Essentially, what I do here, I take my state and I project it on the Fock basis, and modulo square of that quantity will give me the probability of any specific pattern. This is the pattern, N1, N2, N3, and so on up to Nn. So for example, you can calculate and find for some specific state, the pattern 1, 2, 3, 0, 0, 1, and so on. It has a specific probability which is given by this projection modulo square. Okay. Now, how to play a little bit with that and to bring it in a form that you can start recognizing other type of math is a little bit elaborated. And in this paper and in other papers, they have found similar results starting from different kind of settings and mathematical approaches. What we can find is that for any G, any general pure Gaussian state with zero displacements, that probability can be written in this form. Now, these are the squeezing parameters. This is the stuff that we know. This Ni are the members of the photon number patterns. Okay, the important thing is the numerator of that expression. The numerator of that expression takes this, some will say ugly, I will say that it's not ugly, this kind of form, where R is some specific Gaussian distribution, and this H is the covariance matrix of that Gaussian distribution, which is given as a function of the squeezing and the elements of that passive unitary Gaussian U. Now, what I recognize here, therefore, is that the PNR pattern is the mean value of these linear quantities. These are the positions and the momentums of each one of the mode of my fields. Okay, so this is a mean value problem here. I need to calculate, if I want to find the pattern, the probability of the pattern, I need to find the mean value of these quantities under some Gaussian distribution, which depends on everything that happened just before measurement. This is known as the Gaussian moment problem. And also, it is known that the Gaussian moment problem is the integral representation of what they call in math Hafnians. Hafnian of a matrix. So this integral represents the Hafnian of some matrix F whose elements Fij are given by the 2-point mean values, small fi, small fj, where small fi is defined as a complex number, canonical position of my field for the ith mode, plus imaginary unit canonical momentum of my field for the ith mode as well. Okay. It is easy to see that if you sum up all of the pattern numbers and you find them that they are odd, that will be equal to 0. And essentially that is why your whole integral, I mean, this kernel here is even. So if the summation over I for Ni is equal to something odd, the whole thing will become odd. Okay, even multiplying odd is odd. So if you integrate from minus infinity to plus infinity, that will become 0. But if it is even, then this is in general is a hard problem to solve, to find the Hafnian. And we'll see that in a minute. You can calculate the Hafnian F, or equivalently, you can calculate this integral, or equivalently again, calculate this mean value under this Gaussian kernel by using Iserley's theorem, okay, that I will introduce in a moment. Basically, what Iserley's theorem is doing is that he takes many point mean values, like this one, and then they tell you the recipe on how to break that into products of 2-point mean values. Well, I mean, one question is, why do all of these things? I guess that all of us are familiar with the Galton board. In general, what does it do? I mean, you throw like a little ball, and the ball ending up in a specific bin is what we call sampling. So you sample from a specific distribution. You sample from the binomial distribution, and in the limit where the bins are very small and you have many balls, you will get the Gaussian distribution at the very end. Now, in general, a classical computer program that samples from a given distribution, not necessarily Gaussian, any distribution. So I ask you to create patterns using some classical algorithm, and these patterns must follow some specific distribution that I have given you. This problem in general is very hard and scales exponentially with the size of the requested pattern. So that's why we built an optical quantum circuit like that, because this is, if you like, the quantum analog of the Galton board. Here now, these are my balls. These are like the little obstacles you have here, and the bins are the PNRs. So this thing can sample from the specific difficult distribution and give you proper patterns. And this is what we call Gaussian boson sampling. Now, let's discuss a little bit about Hafnians, about a more abstract explanation of things. What is a Hafnian? What is a perfect matching? How that does scale with the number of objects you have. Well, imagine you have a set of objects. I don't even define what these objects are. Some dots, whatever. Okay. I just label them G1, G2, G3, G4, and so on up to G sigma, capital sigma. So I give you this bunch of objects, and I ask you to find what we call perfect matching. What is a perfect matching? Is to connect the objects with a line so that any object is used only once. No more than one line can start or end from any point. Okay. What's the Hafnian? The Hafnian is the problem that asks you to find all possible perfect matchings. Okay. I have an example here. I have 4 objects. So this is one perfect matching. I connect this one to this one and this one to this one. Then I have another one. I have to connect, I can connect this one to this one, this one to this one, and G2 to G4. So I get perfect matching number 2. And the last one is to connect 1 with 4 and 2 with 3. In total, I have that many, double factorial, okay? You just multiply 1 by 3 by 5 if you have more, and so on and so forth. So this is what a Hafnian is. Now, I just rewrite the same thing, but how does the previous example on GBS relates to the calculation of the Hafnian? Well, before I derived a formula that told me that the integral I want to calculate is the Gaussian moment problem, which is a Hafnian. Okay. Now, how can I use these facts to calculate more efficiently what I want to calculate and calculate my Hafnian? Well, there is a small trick here because I have powers on top of my objects, of my F object. I have it 2 times. So to apply Eiser's theorem correctly, I have to relabel. I have F1, F1, F2, F3. Now I will call F1 to be G1, and the other F1 I will call G2. F2 is G3, and F3 is G4. So I want to say that I have 4 objects here, not 3, because that is in the power of 2. Okay. And now I take this 4-point mean value and I find all possible perfect matchings. Okay. And what you see here is an example of Eiser's theorem on how to break a 4-point mean value into a product of 2-point mean values. This is a product, this is a 2-point mean value, this is another one, this is a product thereof, plus the other option, the other perfect matching. So what I want to say here is that Isserlis theorem essentially calculates the Hafnian. It tells you find all possible perfect matchings, then product this with that. Now the green line represents a mean value. So this is a mean value, multiplying that mean value, plus that mean value, multiplying this mean value, plus that mean value, multiplying this mean value. Okay. Now, after you're done, and you have calculated all of those 2-point mean values, which are easier to do than calculating in one go this mean value under the Gaussian distribution, you go back and you say, okay, now look, I have applied my Isserlis theorem by expanding my set of objects using perfect matchings, but I know that G1 and G2 are equal and are equal to F1. So you just label back and you get that your initial Hafnian can be breaking down in a product of 2-point mean values exactly like this. Okay. Here I just state what we examined through example. I just state Isserlis theorem, okay, which says that if you have the Gaussian moment problem, you want to calculate that mean value under this Gaussian distribution, which means exactly this thing. What you need to do is 2 steps. One step is you need to write down F1 N1 times and label each one of these F1s differently. Do the same for all of these. So that way you will get how many N1 plus N2 plus N3 up to plus Nn members within this mean value. And then you apply the actual Isserlis theorem, which tells you that create all possible 2-point mean values, okay, and sum the products, which products you sum over all distinct, you sum over all distinct ways of partitioning 1 up to S objects into pairs. And then you do the product over all possible pairs. Okay. So that is to say that if you do squeezing and if you do some general Gaussian transformation, you can get something like a task-specific quantum computer, which we call Gaussian boson sampling, which can sample from a Hafnian, while a classical algorithm, as the problem scales up, as you have more PNRs and more modes, would struggle to calculate, because classically that program would behave exponentially, while in the quantum realm, it scales polynomial. All of this to say that quantum states of light is something that we can describe very efficiently. I mean, if you think about it from the very strict physics point of view, and you forget about information for a moment, I mean, what is quantum optics and continuous variable systems? Is a field theory. Actually, it's the simplest field. Okay, we know everything. We have solved this kind of field theory. Also, we know that this type of field theory is goes very well with special relativity and things like that. So it's a simple field theory. All of the math we are doing here are based on math that we have learned in standard quantum mechanics. So the only thing you need to do if you want to work or you want to study or whatever continuous variable systems in quantum information science, you just need 2 things. You need to be very good in linear algebra. You need to have some programming skills. I don't say that here, but that is true as well. And then the only thing you need to do is to build intuition by solving problems, by publishing papers, by reading other people's papers, and so on and so forth. Quantum states of light are beautiful because they possess counterintuitive properties. If you like that terminology, counterintuitive. That means that you can have like superpositions, you can have entanglement, you can have quasi-probabilities that have negativities in them, and so on and so forth. And also, they give you quantum advantage, where a prime example in our view, is the boson sampling paradigm and the Gaussian boson sampling application as well. So I don't know if Saikat want to take.
I just have a couple of minutes, so thank you, Christos. So I hope that you got at least a glimpse of the kinds of math that goes behind quantum optics. Somebody had a question about why are these samplers, and I hope my answer is clear. That all these devices, the Gaussian boson sampler, the boson sampler, and Google's IQP demonstration, which was the first so-called quantum supremacy demonstration in 2019, they're all random samplers. They're all Galton boards where every time you push a button, it generates a random sample. In Christos's description, a random sample was just a random click pattern that comes at the output of that Gaussian boson sampler. If you try to write a classical computer code to generate random samples from that same distribution, the time it will take will grow exponentially, with the size of the problem. So, and all of these papers publish these astronomical numbers. Look at this paper from Xanadu. They did a Gaussian boson sampling experiment with 216 squeeze modes entangled with a linear optical unitary. And they estimated that the best available algorithms with the best possible supercomputers in the world will take about 9,000 years to produce one random sample with a distribution that has a certain level of accuracy, but an actual Borealis quantum computer, which is the name of their squeezed light-based the circuit that they have built that requires about 36 microseconds. Very similar results from Jianwei Pan's group in China. They did the Gaussian boson sampling experiment, and so on. Now, you might ask, what are these random samplers good for? Well, I won't have time to go into this, but these are just some still older references. There are more new references you can take a look at. One of the things that came out of thinking about these random samplers, so random samplers can be a very nice building block that can go inside an algorithm. What kind of algorithms? Well, Christos talked about the Hafnian, the probability distribution of click pattern is the magnitude squared of a Hafnian. Turns out you can take a graph, any graph, and map it in a certain way into the covariance matrix of the output of the Gaussian state of the output of the Gaussian sampler, boson sampler, which you detect. And if under that mapping, the probability distribution of that click pattern, instead of a magnitude square of the Hafnian of that matrix, it turns out you can write it as a magnitude square of the Hafnian of the adjacency matrix of that graph. And so with that mapping, you can use the Gaussian boson sampler as a quantum powered graph classifier. And this is something that a lot of people study. People also looked at using Gaussian boson samplers to study molecular vibronic spectra and other applications. Complexity theorists believe that these random samplers, boson sampling, IQP, Gaussian boson sampling, etc., they're not as powerful as universal quantum computers are, but they're believed to be strictly more powerful in the complexity theory sense than classical computers. So I'll leave it at that. And this is really our last slide that, the building blocks that we covered in modules 1 and 2, it was a very, very fast crash course in quantum optics. But we covered linear optics, coherent states, multi-photon states, squeeze states, photon detection, and homodyne detection. In principle, all of these things that you just learned, they all suffice to design quantum optimal transmitters, processors, computers, receivers, sensors, and for all applications in photonic space information processing. As Christos said, the rest is math, less is linear algebra, imagination, and creativity. On the other hand, I hope we were able to also convey that even though we have all these tools at hand, mathematical tools, which help us figure out oftentimes what is the best that quantum physics allows us to do in the context of, say, communication, sensing, or what have you, we many times don't know how to put these building blocks together in order to attain best performance in extracting information in a photon. So hopefully you enjoyed this course, and there are a few more open questions. Let's see if I can answer them live. What's the current status of universal photonic quantum computing, not random sampling? Good question. There are two companies, PsiQuantum and Xanadu, that are building universal photonic quantum computers, fault-tolerant quantum computers. Xanadu is encoding their qubits into the photon using what is called the Gottesman-Kitaev-Preskel encoding, whereas PsiQuantum encodes their qubit using the dual-rail single photon in 2 modes encoding. Both of these companies are making excellent progress. There isn't one computer at this point. People who are proponents of photonic quantum computing, they believe that it's the progress in photonic quantum computing will not be like superconducting or trapped ion or color center-based quantum computers where you build one qubit very well, you really work hard to create another qubit and then connect them and so forth. But when the photonic quantum computers get to fault tolerance, you will get a million logical qubits that will be fault tolerant and universal logic capable at once. We could go in more detail into this topic, and if you're interested, please let us know. Does the hardness proof depend upon using Isserlis theorem? Isserlis theorem really is used to write down the output distribution.
Well, I mean, if you want to apply, if you to apply the Isserlis theorem, means that you need to find all primitive matches, and this is a hard problem in its own mean. Now, there are improved versions. You can circumvent using Isserlis theorem. This is like what one is the first thing that you think of doing. There is an improved version of Isserlis theorem where it takes into account the exponent n1, n2, n3 I had in the slides, but still this improved Isserlis theorem still scales exponentially. It is faster, but scales exponentially as well. So if one can find an improved Isserlis theorem that scales polynomially with the length of the pattern, then that would be great, but I think it's impossible.
Yep. And also the hardness proofs, all of the hardness proofs, they rely on a conjecture, especially for boson sampling and Gaussian boson sampling. The hardness proofs, they rely on a conjecture, but that conjecture being false will imply that what is known as the polynomial hierarchy of complexity collapses, meaning sharply complete, which is the hardest problem. Sharply complete is where you have enumeration problems. You enumerate all possible solutions and work out the objective function. That will collapse to P, which is, people don't believe that's the case. So the hardness proofs are pretty well rooted in the mathematics of complexity theory. The last question is that, do I know about Quix from Netherlands? I'm sorry, I don't. I have heard about a company that Ish Dhan, who was formerly with Xanadu, and Christine Silverhorn, they started. They're also doing discrete variable photonic quantum computing, but using spectral mode encoding. I don't know if that's the company that's called Quix, but there are multiple companies across the world. So I must have missed some other companies.
Is it a photonic company?
It is a photonic company, yes. So Christine,
I mean Quix.
Quix, that's what David is asking. So it probably is, but I don't know of it. So universal quantum computers are an engineering problem now. That's what many people will tell you. I would say the community is pretty divided in what they think about whether quantum computing in general is an engineering problem. If you talk to Jeremy O'Brien, he will say an emphatic yes to that answer to your question, David. He would say you have the quality of linear optical circuits, the G2 of the single photon sources, the efficiency and dark click probabilities of superconducting nanowire single photon detectors. If you look at all of these technologies independently, their qualities collectively are good enough for you to be well within the fault tolerance regime of the Rausendorf-Harrington-Goyal code for measurement-based quantum computing using dual-rail photonic qubits. So yes, it is an engineering problem, but it's a huge engineering problem.
Well, what I would say is that, I mean, apart from math and all of these things, that it's not an engineering problem. I mean, it's something like that. What we need is physicists, computer scientists, and engineers, and complexity people start speaking the language of one another.
That's right. I mean, and that's a good point, Christos. I mean, the question is whether photonic computing is an engineering problem. Well, these two companies, and there are other companies like Orca that Mike mentioned, they have made choices on qubit encoding in the photon, error correction codes, connectivity, and they have respectively found the resource requirements needed to get you universality and reach that. But that doesn't say that there aren't better encodings of qubits in the photon, better error correction codes, and better architectures that might give you orders of magnitude improvement in. So I personally still feel that this field is ripe for a lot of fundamental research. that brings together information theory, quantum optics, and physics together. On the other hand, the field is at a point where certain ideas are ready for an engineering acceleration. I think we are 10 minutes past the hour. I would say let's go ahead and end today's lectures. Hope you enjoyed the course, and chat window, there's a direct link to the evaluation survey. Please go ahead and fill that out. And Brianna, do we need to keep the Zoom link open, or people can just take the evaluation survey and you will get the answers when they are done?
Correct. Yeah. So we'll go ahead and thank you, Saikat and Christos, for taking the time to put together the short course and taking the time to teach it today. There are some errors in the slides that we shared today, so we will get updated copies issued with the recording. So I will go ahead and end now, and thank you all.